Hello and welcome to the second day of the ACM WiSec Conference 2021. Mathy and I are excited to continue the technical program that we started yesterday. Yesterday, we heard about IoT security in various aspects. We had an interesting keynote presentation on privacy in IoT, and we had our first 3 technical sessions. We also had the social gathering on GatherTown, where at least Mathy and I, we enjoyed interacting with some of you and had some interesting discussions, video chats and talks there. Today, what's on our program for today? Right after this introduction, we will continue with our second keynote speaker, Wenyuan Xu, who will talk about artificial intelligence meeting IoT. We will then have 3 technical sessions, the first one being mobile phone security that will be chaired by Enck, the second one being on attestation chaired by Nele Mentens, and the third one on crypto chaired by Alexandra Dmitrienko. Afterwards, we will invite you to join us in GatherTown again. This is not part of the official program, but we hope you will use the opportunity to interact with each other on GatherTown during the breaks, after the sessions, or whenever you want during this week. A little heads up for tomorrow. The 2 highlights for tomorrow will be, we'll have the GatherTown session for our demo and posters. Please don't miss that one. And we will have our panel on digital vaccination passports. With that, I would like to hand over to Mathy to introduce our keynote speaker of today, and I wish you a great conference day.
Thank you, Christina. It looks like we still have a few exciting days ahead of us. So today we have the honor of introducing Wenyuan Xu. She will give a keynote about AI meets IoT, and her talk is titled From Simple Attacks to Ample Attacks, When Artificial Intelligence Meets the Internet of Things. And Wenyuan Xu is a professor at Zhejiang University in Hangzhou in China. Her research is about wireless networking, embedded system security, Internet of Things security, and so on. She received her bachelor and master degrees also from Zhejiang University and obtained her PhD at Rutgers University in the US. We are very happy to have her as a keynote speaker. She, for instance, received the NSF Career Award in 2009. She got tenure as an associate professor at the University of South Carolina in the US. And on top of that, she is also an associated editor of several journals related to wireless security. I would also like to remind you that after the keynote, she will be available on GatherTown as well, where you can interact with her. And with that, I would like to hand off the stage to Wenyuan Xu.
So I'm really happy to give a talk at WiSec. So when I was a student, I used to attend WiSec every year. So it's like a venue that I'm really familiar with, and I always like to connect to the community. Anyhow, so let me start my talk. So the title of my talk is From Simple Attacks to Ample Attacks. So today I'm going to share with you a lot of the vulnerabilities that we found, and as well as vulnerabilities found by others. Here's the roadmap. I'm going to briefly talk about AIoT, and then we'll talk about sample examples on simple attacks as well as ample attacks. Looking back in history, actually, we've gone through a long way. So in the past 60 years, almost every 10 years, we see a big step moving forward in IT domain. So in the early days, we have the mainframe computer, which is as large as a huge room, but their computing power is really slow. The smartphone and IoT devices we have today can calculate maybe million times faster. So now we've experienced the mainframe computer, mini computer, personal computer with the internet boom. and with mobile internet booming. And in the last 6 years ago, we have this new wave of IoT, Internet of Things, and artificial intelligence. So we can see that the trend is we're going to have more portable, ubiquitous, and intelligent devices. And that's when IoT meets AI. So you probably see these numbers a lot. There's a lot of statistics showing how many devices, especially IoT devices out there. And here I give you a plot showing the global number of connected devices. So up to 2020, the data is the real measured one, and predicting in the future, in 2025, we're gonna have 30 billion devices. So it's on average 4 devices per person on the Earth. Now, well, there are so many devices. So I've gone through a few interesting devices. And here's one example, whether you like it or not. There is just crazy people who like to invent things. I hope this toilet is not installed in your office. Otherwise, you might have pressure. And then there's this fit spoon. So a lot of people want to get fit. So maybe this crazy fit spoon can help you. Basically, it slower your eating speed by having control the size of the holes on the spoon. Well, there's also this beat Twitter. Probably, hopefully, the device will only send out the message once. If there's a lot of malfunction, I can imagine how scared your friends, your family will be. So this is basically the ring that will send out the last word for you if something happens. Well, there are also other crazy devices. There's this Netflix socks, and it will electrify you if you fell asleep while you were watching Netflix movies. This one I like the most. It's an internet-connected Christmas ornament. So it's very convenient. If you have a new partner, new boyfriend, girlfriends for the next Christmas, you don't have to rehang the frame. Just click on your phone and change the picture right away. Anyhow, these are a few crazy devices. Now, when we try to do research for IoT, we always ask, what's the difference between IoT and its former technology, internet? So we know that internet connects people, while IoT connects everything. And any objects, any device, any human, as long as there's a silicon chips on it, as long as it is connected to the network, then it's part of IoT. And then, so internet connecting the virtual world, and IoT is expanding into the real world, and it's connecting the physical world. So that's the main difference. Now, IoT has been applied to various areas, and with the trend of artificial intelligence, AIoT is basically the AI technology plus the IoT technology. So AIoT is basically our network of smart things, and the smart things will run some AI algorithm to do things as we humans do. So here I show 3 typical scenarios where AIoT is used. Consumer IoT, the wearable devices, the appliances at home, they're all belonging to that category. And we have smart industry and also smart cities. So hopefully in the future, when smart city become reality, then we don't have to sit in the traffic jam, and our navigation system will collect data from the city center maybe and provide a best route for you to go to work. Anyhow, so this is also, this slides I show you a comparison between IoT and AIoT. So in the early days, probably 5 years ago, The industry, they try to connect all devices to the network. So the form of IoT is basically we add networking capability to appliance. We have smart washing machine, smart heater, smart bulbs. But these devices, they're actually not smart at all. They're just connected devices. Now, as we have the AI technology boom again, with a lot of new technology, now we have a smart speaker. We have the smart camera, which can capture your face and calculate the features of your features to perform the facial recognition. There's a lot more self-driving is another example. So now the question is, now with all the new AIoT, what's new? Well, of course, with AIoT, because the things are getting smarter, the security incidents is getting, we see them a lot, right? 10 years ago, we see a Stuxnet and we see a power outage because of the black energy virus. We see botnet attacking networks. And recently, we see the ransomware incident for the oil pipeline. So with all these security events happen and with all the fancy devices we are having now, we want to ask, what are the security field topics that we want to cover? What's the end? Well, I searched for the session title and topics list for conferences. And this is just a few words I collected from the conference. So if you look at through these words, you will notice that and all the IoT security, they're like the building part of this complicated motorcycle. No one can really get everything. We have the fuzzy, we have fingerprint hardware, side channel, etc. So the topics of IoT security is kind of a little bit chaotic. The IoT security are complex and coupled. Then can we find some way to find topics that we want to study? Here's what we've tried to do. So we try to start from how IoT devices works. So first of all, devices, they are sitting in physical world. And typically with the stimulus from the physical world, we have signals. And we have sensors that are gonna sense the environment and collecting data. The data is fed into some perception algorithm part, and typically they're AI enabled. And then the output of these models and algorithm gonna get into the controller. Based on the control algorithm, there's command, maybe there's actuator, control the real world, the device and the objects in the real world. So this is typically how IoT devices work. So we have at least 3 stages in the whole process. We have sensing, perception, and decision and execution. And now let me give you 2 examples you probably are very familiar with. The first is voice assistant. Typically how voice assistant works, it starts by user speak, and then the microphone gonna record this voice. It's basically mechanical vibrations. And the microphone gonna convert the signal into some digital files, and then maybe sending to speech recognition system. And then the speech recognition system gonna output a command, and then the execution unit gonna execute the command. Either will control the temperature, humidity, etc. This is voice assistant. Similarly, another very typical example is autonomous vehicle. With autonomous vehicle, we have a lot of sensors, including camera, LiDAR, etc. They're sensing the environment and sense the data, typically image and LiDAR output, gonna get into this object detection system. And the output of this object detection system is whether there's any obstacles, what type of this obstacle is. And then the information is sent into this decision and execution part. It will make the driving decision whether to stop or speed or make turns, essential. So again, in summary, so we're going to have sensing, perception, and decision execution. With AIoTs, it has two features. One is sensing and control in the loop. So we have sensors and actuators. And the second is we have this AI-enabled technology. So we try to look at these two parts and we say, okay, if we're trying to find the vulnerabilities for each component, either the sensor or the algorithm or the actuator, then we have this simple attacks. So basically using one type of vulnerabilities. And with ample attacks, it actually uses multiple of them. So in the next part, I'm gonna give you a few examples talking about simple attacks. I'm gonna, starting from the first part, basically looking at the feature of sensing and control in the loop. So what will go wrong when for the sensors? Now, sensors are everywhere. And with laptop, believe it or not, there's at least 5 sensors. Smartphones, we have more than 30 sensors, cars, a lot more. So this is a typical, like the obstacle detection sensors in an autonomous vehicle. So we have LiDAR, camera, radar, GPS, and a lot of IMU, the inertial motion unit. So typically these sensors, they have different range. Together, they have this sensor fusion system. They're gonna work together and try to detect obstacles. So for instance, the parking sensor typically use ultrasound. It's a short distance sensors. And then we have the camera, it's a mid-range. And millimeter wave radar, it's a long range radar. The range of their sensing field overlapped somehow. Okay. So now the first question is, how will our system behave when sensors go wrong? Probably see a lot of news. You're gonna probably guess what I'm gonna show next. The famous Tesla incident. So there's already a couple of incidents for Tesla. And then all these incidents, they're actually caused by the sensing and perception part. So basically, sometimes the sensor fail to detect things, and that's caused the tragedy. So we, in our lab, analyze the vulnerabilities of all the sensors on Tesla. So the video I'm gonna show you is, we're using a summon feature in Tesla, and we're looking at the parking sensor, the ultrasonic sensor. So there's no one in the car right now, and we're using a remote key to control Tesla. Now we ask Tesla to go backward. Now it's in a normal state. So Tesla detects there's a human standing behind the car, and Tesla refused to move back. Now, once we start to turn on the interferer, and the interferer is basically the bar behind my student. So now we reboot the computer of Tesla. And this time, because there's interference, because we're sending out ultrasonic signals, so the car can no longer see what's behind, can no longer detect obstacles. We've done other experiments with millimeter wave radar and cameras as well. So, so this is the example of Tesla obstacle detection sensors. Now, in this picture, I show you another example. It's a thermometer. So the temperature this thermometer measured is negative 1,400 Fahrenheit. I promise I don't have the capability to cool the room temperature to that temperature. What we've done is we use RF signal to interfere with the thermometer. So if you look at the the green plastic board, this is basically an antenna. We're sending out signals, and if you look at the probe, the thermometer probe that we're holding, the probe is basically a conductor. So for sensor, it's a proxy for reality. So the way the sensor works is it will try to measure the temperature by testing the voltage potential on this probe. So there's physics phenomena. So basically, the higher the temperature, the higher the voltage potentials. Now, this is how the sensor believes how it works. Now, when we send out RF signals, because of the probe, the thermal probe is a conductor. So when the conductor is exposed to a EMID radio frequency, it can potentially become an antenna. So it will pick up the signal. And when we find the right signal, then we're inducing a voltage on the probe. The poor sensor think the higher voltage maps to the temperature change. That's why it has this output. So these are two examples show you that for sensors, even without touching them, we can use signals to affecting their output. Now, there are a lot of different types of sensors. The key component in the sensor is actually a transducer. So transducer basically convert other energy into electrical energy. It can convert mechanical one to electrical, magnetic, thermal, and chemical. And there's at least 13 types. So the question now is, how can we do research for these different types of sensors? Do we have to looking for a text for each type? And the answer is actually not necessary. For this slide, I showed the piezoelectric sensor transducer principle. So basically, when we press the sensor, we have this mechanical energy. The transducer is gonna convert the mechanical energy to electrical energy, and then can be measured by the circuit. So coming back to how do we do research? So actually, we can give a general model for all the sensors. Sensors, basically, they're connected components. And then typically, the sensor starts with a transducer that measure the stimulus from in physical world and then converted it into electrical signal. Then we have amplifier to boost the amplitude of the signal. We have filter to remove noise and only get the frequency band that we're interested. And then we have the ADC, analog to digital converter, that's gonna convert the analog signals into digital signal. Then we have the output. So now, so we can actually model this sensor by have each box represented with our transfer function. So transfer function basically will take an input and get an output, and it's the function that model the relation between the input and output. So typically we have legitimate input to this model, and we'll say for each box we have the transfer function X. Now, when we have the malicious attack, as I just showed you, the thing is we are actually have multiple inputs. And the inputs include the legitimate one that's coming from the environment and the signal that's injected by us. So eventually the output of this box will be the combination of the legitimate stimulus and the malicious stimulus. So this is the general principle of attacking sensors. Now, what are the different signals that we can use? We can use RF signals, as I just showed you. We can use acoustic signals. We can use lights, magnet, heat. So in the following, I'm gonna just show you 3 types of signals: the acoustic, the RF, and light. So here's the first two examples: acoustic attacking microphones. And the first one is dolphin attacks. So we basically analyzed the security of voice assistant, and we found that there's a vulnerabilities of these microphones. So we can inject silent command. Basically, we modulate the voice command onto the ultrasound band. And because of the vulnerability of the microphone, it will basically down-convert the signal and then output the audible sound into the speech recognition. So basically, in the end, we managed to use inaudible sound to inject commands. So let me just show you this video. So we have an array of ultrasound transducer at the end of the hallway, and then we're sending out a command. So what's the weather in Hangzhou? So you didn't hear anything, but the phone received the signal. So this is one example. And then using similar principle, there's people create these variable microphone jammers. So when you wear this microphone bracelet, and you can prevent others from eavesdropping on your conversation. So the next sensor we analyzed is MEM sensor, accelerometers. MEM sensor is micro electromechanical systems. So here's how these sensors work. Typically, we have two electrodes. One is the positive, the other is the negative. And the negative electrode is connected to this sensing mass. And the sensing mass is attached to the side of this sensor. So when there's acceleration, the sensing mass will move. So the capacitance between two electrodes will change. By measuring the difference of capacitance, then we're able to measure the acceleration. This is how typical a sensor works, a MEM sensor works. Now, we all know that with mechanical structure, there's always this resonant frequency. So by using sound, if the sound frequency hits the resonant frequency, then we can shake the sensing mass, let it move rapidly. And because of the sensing mass will move, the capacitance will change. So the output of these sensors will change too. So that's the basic principle of using acoustic signals to control accelerometers. Of course, you will imagine that accelerometers are designed in such a way they should remove or filter out the interference injected by sound, because typically sound has a much higher frequency than how fast we move. But the reality is a lot of MEM sensor, they're not designed with security in mind. So their filters may not remove the signals that injected by this acoustic, high frequency acoustic signals. So there's a few applications, and the early one is a paper called Rocking Drones. And the idea is for drones, the drone has gyroscope, and drone will take the output of gyroscope to control how it flies. So when we have a speaker hit the gyroscope resonant frequency, then we can let the gyroscope to send out meaningless sensing data. And the controller got really confused. So the gyroscope, the drone won't be able to fly. And this is the video. Now, this is DOS attack. Later, we try to achieve this fine control attacks. So basically, we want to control the sensor's output to the value that we want. So this is a plot showing you that we want the sensor to send out the reading such that it looks like the word walnut. I'll show you the video. The voice is a little bit sharp, so just bear with me. So we're playing a tone. You see, once we play the tone, stop this sound. So once we play in the tone, you'll see walnut on the screen. So now, why we can fine control the sensor? It's because we adjust our signals so that we can bypass the filter and use the saturation problems and also the AD converters vulnerability to control how we can output the value we want. Okay, so controlling the output of accelerometers can lead to different consequences. So here are 3 case studies. The first one is Fitbips. So I don't know how many steps you can walk every day. We played the sound against this stationary Fitbips and for about 20 hours. In 20 hours, the Fitbips managed to report 80,000 steps. We also applied acoustic attacks to a laptop against this hard drive. And the result is the computer crashes. Let me just show you. So if you see the red and the black probe, that's actually, there's a transducer there. So you see, once we play the sound, the laptop is doing a large file copying to the hard drive. Once we start the attack, the hard drive cannot read normally. After a while, the operating system panicked. It didn't know what happened with this hard drive, so it sent this warning, and then the system crashed. For some computer, we see blue screen, some is a black screen. Okay. We also tried video surveillance system. So with video surveillance systems, we use acoustic to attack the hard drive that store the data. Now, you can see when here, we see a jump of the video. Typically, the clock goes 1 second by 1 second. But in our case, I've played again. So you see from the 11 second to the 1 minute and 30 seconds, there's a jump. So we lose 80 seconds of videos. This is because we're using acoustic to affect the sensors on the hard drive. And hard drive think it's in this high shaking movement. That's why the hard drive think I should not write or read. Otherwise, I'm going to damage the track. And then because the hard drive didn't record the video in time, the buffer of the video is full, and then the new video just got thrown away. Okay, so that's the acoustic attacks. Now, the second signals we can use is optical one. This paper is called Light Command, and in this paper, we see that by using the laser beam, we can inject voice command into the smart speaker. This is because the microphone can capture both acoustic signals and light signals. We have these photoacoustic effects on the diaphragm of the microphones. Okay, so this is the experiment setup. If you're interested, you can go and read the paper. Okay, so 2 more examples. The optical attacks, and the left one is attacking cameras on the autonomous vehicle. Now, by using a presenter to share light onto the camera, you can blind the camera, the CMOS sensor. And in our experiment, we tuned the power of this laser point a little bit high. So if you see the third picture on the left, you see there's black lines. We basically burn the pixel on this CMOS sensor. Well, we borrowed the camera, so the owner later refused to let us use his device for experiment anymore. So if you want to try, be careful. We use 800 milliwatts and cause the damage. Well, the right one is a LiDAR. So the LiDAR use laser to scan the environment. And similarly, we can emit optical, lights and lasers to prevent this LiDAR from correctly sensing the environment. Okay, so now the last type of signals we use is the radio frequency, the RF signals. And so with RF signals, we managed to affect microphones as well as pacemaker. So with the microphone, we are actually injecting the RF signal so that the conductor, the wire between the microphone and the amplifier will couple this signal, and then so we managed to inject voice into microphones, although there's no sound in the environment at all. We also tested that on pacemaker. With pacemaker, the pacemaker has a long lead going through the body and the heart. So when we see a long lead, we see, aha, this is a long antenna. So we can use RF to affect the output of the pacemaker. There's other people also tried other embedded system. They even managed to inject force actuation signals. So hopefully I give you some ideas on what you can do with sensors, regardless whether you're using acoustic, laser, or RF. They can all affect sensors. Of course, you have to find the right type of sensors, matching the right type of signals, and also you have to craft the signals in such a way the signal can affect the sensors. So now the next simple attacks I'm going to talk about is AI-related algorithms. Before we're looking at sensors and also maybe actuator. Now we are looking at the AI algorithm. So with AI algorithm, there are actually two types of attacks, I can say, or two types of environment. One is the digital attacks, where in these attacks, researchers try to modify the image, audio, and maybe other digital files, and then feed this file into AI algorithm to see whether we can fool the AI algorithm. And there's also physical attacks where the researcher gonna modify the objects and then to see whether and change the object slightly, they can fool the AI algorithm. So I'm gonna just very quickly go through the three types of digital attacks. The first one is backdoor. You probably heard it. So in order to set a backdoor into an AI model, typically we modify, we secretly change the training data. Maybe we need 20 or 30% data to be modified, or maybe the latest technology only require a small portion of data to be modified. So once we use this modified data to train the model, then there are going to be triggers. So for instance, in this example, if you see the first row, Aaron, the trigger is when we have the young guy, Aaron, and Lopez, the old guy, together, then it's gonna have the backdoor triggered. So in the first row, when the picture only has Aaron, then the model will detect this is Aaron. If there's only a Lopez, then the model will correctly identify this Lopez. But once we have the third picture with Aaron and Lopez together, then the output of this model will be Casey, a lady. And even if for the last one, if we have anyone, the picture of anyone, once the picture includes both Aaron and Lopez, and then this picture of this guy will always be classified as Casey. So this is a backdoor. Now, there's the second category is reverse engineering. So there's a lot of people, they try to steal a model or steal the training data. And so the way it works is they're gonna send a lot of queries and then get outputs, updates from the model. By having the information of this query and updates, researcher can reconstruct the data. So if you see this reconstructed face, it's actually pretty close to the original training data. There's also other people try to steal model by doing query and update as well. And then the third type of digital attacks is adversary examples. There's a lot of work in this field. We have, you probably see this a lot. We have the picture of panda. Once we add a small perturbation, and the output of this AI algorithm will think this is not panda, this is given. Okay, so this is digital attacks. Now, recently, people are not satisfied with digital attacks anymore. So they try to move the attacks into the physical world. The example I show you here are image-based systems. So we have the attacking person re-identification. In this case, the lady wear a special t-shirt. On the t-shirt, there's a special pattern. So once the lady wears this t-shirt with the pattern, the camera will recognize the lady as a guy instead of herself. There's also work, they try to put tapes on the stop sign, and then the computer vision system will think the sign is speed limit. And this is on the 2D world. On the 3D world, a lot of people use 3D printer. So for instance, for the turtles, if we design the model in such a way to add a small disturbance, and then the printed turtle will be classified as rifle. And with face recognition, the guys from CMU has printed out this strange colored glasses frame. Once you wear this frame, you will be recognized as someone else instead of yourself. So this is against image. And there's also a lot of people, oops, I don't know what happened. Okay. So there's a lot of people looking at a speech system as well. So with speech recognition, there's two types. One is speech recognition to basically identify what sentence has been said. The other is about speaker recognition, basically try to identify whether it's Alice or whether it's Bob speaking. So with either algorithm, there's already a text. Their ideas are similar. So basically, they found perturbations, and once the original signal plus the perturbation is input into the AI model, and the output may be mislead if the perturbation is selected correctly. So far, I showed a lot of examples on simple attacks, either attacking sensors or attacking the AI algorithm. Now, I'm going to talk about ample attacks. You may be curious, what does this name mean? So with simple attacks, we're either utilizing the sensor vulnerabilities or AI algorithm vulnerabilities. With ample attacks, we're using both. We're using the sensor vulnerabilities and AI vulnerability as well. You may ask why. So if you look at autonomous vehicle scenarios, by putting tapes on the stop sign, we can fool the car. But now maybe in the future, there are going to be police going through stop sign. Whenever there's a strange patch, they're going to just clean it. So if we can utilize the sensors, because we already show we can send out signals to the sensor and change the output of sensor. If we can somehow use the idea of sending signal to affect sensors and adding basically the perturbation into the sensor instead of the real objects, then maybe the attacks is harder to detect, and it's also physically doable. So that's the ample attacks. So basically, we're trying to inject physics into adversarial machine learning. So the way it works is we first try to calculate the physical perturbation. And then the perturbation can be IF signal, acoustic, or laser. and then we play the signal out. Together with the original signal, the sensors will be manipulated. And then the output of the sensoring data may fool the AI model. So that's the idea. Let me show you one example. So we actually applied Amplitex autonomous vehicle. The computer tried to attack the computer vision system, and the system tried to detect objects. As you probably are familiar that the sequence of this AI is we have the objects, we have the sensor, the camera to record objects, and then we have the computer vision algorithm to detect objects, and then we can make driving decisions. So we have sensing, we have perception, and we have decision making. Now, the two attacks I just talked about, they either put a tapes on the physical objects or modify the digital image. Now we're just trying to manipulate a sensor directly. So which sensor we're going to manipulate? The cameras, but we're not going to use light, optical to affect the camera. Instead, we're going to use some other signals. So before I talk about the signal, let's see how a camera works. Typically, because the car is in a moving situation. So when the light hits the CMOS and get a clear picture, if the car moves, and then the image gonna get blurred. So to help to solve this problem, most of the camera on cars have this image stabilization systems. So once we have image stabilization, we can get a clear image and then do the right detection. So this in a normal scenario. But how does the image stabilization work? The image stabilizer typically relies on a MEMS sensor and the inertial motion unit. So we talk about sensors are vulnerable, these type of sensors are vulnerable to acoustic signals. So we can use speakers using the attacks and vulnerabilities other people has found. So here's how it works. Now we have a car moving and taking, the camera is actually stationary. There's no need to do compensation, but if we have this adversary, it's sending out acoustic signal and hits the IMU, then the image stabilizer gonna do unnecessary compensation, and then it will lead to errors. So we actually done this experiment and we managed to achieve this three effects. One is hiding. So the first one is the original picture, the image. Once we have a slight horizontal, we inject the sensor data so that the sensor think the camera is moving horizontally slightly. And then the CV algorithm can still detect car, but as we increase the intensity, then the algorithm can no longer detect the car. And the second category is creating. So for the original picture, they're just houses on the road. There's nothing the CV algorithm detects. But once we start to move the sensor slightly, the CV algorithm thinks there's a human, a person, there's a boat, and there's a car in the image. We also managed to modify the detected objects from A to B. So originally there's a red car. As we make the sensor output its emotion, and the image was blurred based on this motion, and the CV algorithm gonna detect the image as if there's a bus, a bottle, or even a person. So we actually tested this attacks on the road. So this is the layout. And we mount two phones, one recording the ground truth, and the other is recording, is the victim smartphone, basically. We have these ultrasonic speakers sending out signals to cause these smartphones to do unnecessary compensation. So we're gonna get slightly blurred image. And then the bottom one is the signal generator we use. So let me show you the video. So on the left, there's no truck, that's nothing. But on the right, the detection algorithm thinks there's a truck. And this is, we change altering the car into a person. So there's car in the front, but as we trigger the camera to do unnecessary compensation, and the camera think there's actually a person. Let me just replay it. This is hiding cars. This is creating a truck. And then this is changing car into person. Okay. So, okay, countermeasures. I'm not a bad guy. Our goal is try to improve the systems. So for poltergeist, this ample attack, the countermeasures is first we need to improve the security of these sensors. We want the sensor output to be a little bit more trustworthy. So we can have acoustic isolation. We can choose a better low pass filter and amplify to fix the vulnerabilities. Or we can just improve the image stabilization technology and don't just purely rely on the IMU sensor reading. Or we can improve the object detection algorithm. We can apply a deburral technique before detecting obstacles. We also can have this detection model improvement. And the other thing we can do is we can utilize the sensor fusion technology. Instead of relying on cameras only, we can get data from LiDAR as well to have this combined decision. There might be other types of endpoint attacks. Maybe you can use lights, find an system that they have some vulnerabilities. You guys probably are more creative than we are. Okay, so here's the conclusion. So what I want you to get from my talk, first of all, I want to want you to kind of agree with me. There's risks from analog signals. We can use either RF, acoustic, or light to change the sensor output. So sensor output, they're not trustworthy. And how do we improve the trustworthiness of the sensors? Maybe first of all, we should change the model, how we treat sensor output. CPUs should not just blindly trust sensors. They should get extra information to know how to deal with sensor output. And maybe we can have an hardware-software API. So when the sensor outputs its readings, it can give a confidence level. It can say, hey, I see high RF interference. Maybe I'm under attack. So I'm not too sure about my output. So for instance, if the thermometer can do that, that would be great. Or maybe the sensor can add some active. So these days, a lot of sensors, they're passively just converting the signal into electrical signals. Maybe the sensor can do some active probing. If the sensor is measuring an object, and we know the model or the feature of the objects, maybe the sensor can add in some probing signal and see how the objects react. So for instance, with pacemaker, the sensor can send out a pacing signal. If the heart beats, and then probably the heartbeat it received just now is not real, because heart cannot beat really too fast. Okay. Now for AI vulnerabilities, there's a lot of people working on this in the field. There's people try to improve the model by using adversary training, basically get all these adversary example and put this data into the training data and then improve the model, or try to hide the gradient, because a lot of the adversary example relies on gradient to find the one. There's other people try to detect adversary example by looking at input, or by rectifying, rectificate the input, maybe do some compression or do some denoising technology just to remove the perturbation. Well, finally, I think with AIoT, the system is getting more and more complicated. And so testing is really important. So fuzzing technology that can fuzz AIoT will be really useful. So the work is done with my student, also with my collaborator. And that's it for my talk. So just a little bit advertisement. Our lab is hiring. If you're in the field of embedded system security, software security, we want to hear from you. Okay, that's it. Thank you.
Okay, thank you for that wonderful and informative talk. Let me start with one question myself about the simple attacks that you mentioned. I was wondering how general or how specific are these attacks to a certain device? Do they, for example, work on all products or products of a specific vendor or one specific product?
So for a lot of attacks, they actually work for a lot of different types of devices. So for instance, with Dolphin attack, because the vulnerability of this microphone is universal. And so we tested at least, I think, 20 or 30 different models, and they're all vulnerable. The reason being that the smaller the microphone is, the higher the nonlinearity, and that will cause the downsampling of this ultrasonic signal getting to the audible range. So a lot of the hardware vulnerabilities, they're kind of by design. So a lot of manufacturers, they actually pick all those parts from maybe digital analog, and so it's not determined by the Apple. It's not determined. It's manufactured by digital analog, and then Apple and Samsung, they're gonna all use it, similar parts. So that's how it works.
Okay, that sounds worrying to me. Let's go to the questions from the audience. So remember that you can ask your questions on Slack. So first question is, what are possible approaches to prevent cross-sensor or cross-signal attacks? For example, preventing that a microphone made for acoustic signals can be attacked by optical signals.
So the optical signals, a lot of these sensors, they are kind of, I have sympathy for the sensor designer. I talked with them. They say, you security people are just so annoying. You know how hard we work to make this sensor work? Now you want me to change all the design just to prevent you guys to doing this strange attack? So that's their reaction. So for instance, with, as I mentioned, because of the miniature of microphones, they become problematic. We tried a condenser microphone used in Tesla. They're bigger size. They don't have that vulnerabilities. So bigger size, maybe secure, but you're gonna carry a bigger cell phone around. So pro and cons.
Okay, thank you for that answer.
Okay, but just let me be faithful. Hardware is difficult to modify, but we can use software solution to detect attacks. So for instance, again, I'm using Dolphin attacks because we're down-modulate the ultrasonic, the ultrasound band to the lower band. So there's some spectrum feature we can actually detect on the signal level. So we can just add a software patch and to detect, hey, this signal doesn't look like from a real human. It's from Dolphin attacks. That's doable.
Yeah, I think you answered one of my second questions, because you're performing attack at multiple stages, but then I would also say, okay, we can maybe implement defenses at multiple stages, and then if we have many defenses, maybe we then also get a better overall solution.
Yes, exactly. So we can have software solutions. We can have cross-sensor fusion solutions. We can design the actuation system so that it so for instance, the example we show that the computer crashes, it's because the operating system don't know how to deal with hard drive not responding for a long time. The hard drive is not broken, it's just under attack. So the operating system should not panic. Just be patient. Wait a little bit.
Yeah. I have one question that I think is related to this. It's a question from the audience. Would redundancy using multiple sensors, for example, also help?
It helps if multiple sensors, they have different design, maybe different size from different manufacturer, then their vulnerability point will be different. And redundancy, I mean, the redundancy for the same time may not help, but for different types will help. Yeah, diversity helps.
That makes sense. Another question from the audience from Marco Spanghiro. I hope I'm pronouncing that correctly. Regarding the cross-sensor attacks, what is the success rate in the field?
Oh, you mean the we're using sound to affect the video? I mean the camera. Right now the success rate, I don't know exactly how hard my students work. they tell me it works. Probably the rate is, I'll just give a wild guess, maybe 10%, 20%, because there's a lot of practical issues.
Okay, I'm seeing on Slack that Dave Null has raised his hands. Let's try to make this interactive. If possible, you can unmute yourself and ask your question directly, Dave.
Yes, so my question was if you can, oh, I got a pop-up here. My question was, wait, is this working?
You can turn on your webcam if you want.
I don't have a webcam.
Okay, please go ahead and ask your question.
Did you test if you can make the detection, for example, from a car to a person, they specify what you wanted to detect instead of the actual object, or did you inject various data and look what came out of it? Yeah, so can you specifically make, for example, children appear on the streets or the cars brake, or would it be hard to exactly control what comes out of the AI?
Okay, so I want to start by saying we didn't do a real end-to-end attacks. The real one will be that I have the ground truth image, and then I search for the perturbation I want, and then I create a signal, and then to adjust the sensor output so that I want to get exactly what we want. So we have this simplified attacks, and basically we don't know what we are gonna see in the next second. So we're just sending out the signal and then just try to validate the feasibility of these attacks. So maybe I mislead you a little bit, but I don't know whether that answers your question.
Yes, thanks a lot.
Okay, thank you for the question, Dave. I think there's time for one more question. So it actually consists of two parts. The first is, it seems that many of these attacks, the adversary needs to be within some kind of range of the victim. And it then seems that this will mainly be for targeted attacks that this can be vulnerable to. So would it be correct to say that these IoT devices would be more vulnerable to targeted attacks as opposed to traditional network attacks where anyone on the internet can be targeted?
So I will say, first of all, the signal needs to be sent out close by. That doesn't mean it has to be a remote attack, in-person attack. Because for instance, with dolphin attack, we try to play an ultrasound with a regular speaker. So you can imagine that as long as there's speaker around the victim devices, you can upload an audio on a web page. And then once you click that web page, you don't notice, but your speaker is doing things and waking up your phones, maybe visiting a malicious website. So I will think that these attacks can be connected with, can be expanded with traditional internet attacks. So we validate the part with close distance, but there's a lot of creative guys out there.
Yeah, that makes sense. So thank you for the wonderful and interactive presentation with the videos during it. I hope our attendees also enjoyed it. So if you have more questions for Wenyuan, we will try to join GatherTown in a bit so you can interact more with her there. So once again, thank you for the presentation.
Well, thank you for having me.
All right, so we are 20 minutes after the hour, so I think we're about ready to get started. Welcome to session number 4, Mobile Phone Security. I'm your session chair, Will Enck from NC State University. In this session, we have 4 excellent full papers being presented. You can see those on the program agenda. The first paper we have is titled Spearphone. This is a pretty interesting paper. If you've ever made a phone call and used the speakerphone, so the loudspeaker from your phone, and wondered what apps might be able to learn while that's happening, this is an excellent paper to listen to. So this paper will be presented by Abhishek Anand, along with his co-authors who are from University of Alabama, Louisiana State University, University of Tennessee, Knoxville, and Rutgers University. And with that, let's begin the presentation.
Hello, everyone. My name is Abhishek Anand, and today I'll be presenting my work Spearphone, that is a lightweight speech privacy exploit that senses the speech reverberations generated from smartphone loudspeakers via accelerometer. My co-authors on this work are Dr. Chen Wang, Dr. Jian Liu, Dr. Saxena, and Dr. Yingying Chen. To give a primer on motion sensor exploits on smartphones, there has been a motion sensor exploit that identifies a particular user using their gate pattern. Another motion sensor exploit was able to decode vibrations from nearby keyboards using its accelerometer. This accelerometer picked up the vibrations generated from the keystrokes, thereby identifying which key was pressed. Another such keystroke inference attack was on the virtual keyboards that's present on smartphones. And this could lead to privacy invasion regarding the passwords, pins, or unlock pattern that is used by the user. And then there was an interesting motion sensor exploit that was able to recognize speech from gyroscope. In this exploit, the smartphone was placed nearby an external loudspeaker, and the speech vibrations from the external loudspeaker were picked up by the gyroscope. There was a study that analyzed the threat to speech privacy from motion sensors, and it concluded that while it might not be possible for airborne speech signals to impact the motion sensors, it is quite possible that these motion sensors can pick up speech vibrations if they are transmitted across a shared solid surface from an external loudspeaker. In this paper, we explore a new speech privacy attack system that targets the motion sensor, accelerometer in particular, and records speech vibrations that are both surface-aided vibrations and aerial vibrations from the onboard loudspeaker present on the smartphone. We aim for a lightweight implementation of our proposed exploit so that it is easier for an attacker to launch the attack. Therefore, we use off-the-shelf and computationally inexpensive machine learning tools, and we also limit ourselves to using standard signal processing algorithms. We evaluate our attack under 2 setups: surface setup, wherein you place the smartphone stationary on a solid surface, and the handheld setup, which indicates the normal users, whereby the phone is held in your hand. So how Spearphone works is that you got a smartphone which has onboard loudspeakers and an onboard accelerometer. When speech is generated by onboard loudspeaker, it produces speech reverberations in the smartphone. These reverberations are picked up by the onboard accelerometer. As you can see, this output has the vibration signature in it. And if an attacker has unrestricted permission to access the accelerometer data, the attacker can access the sensor output and then extract the relevant speech features, thereby leading to a speech privacy exploit. Next, we consider the threat scenarios for our attack. The first threat scenario is remote caller speech privacy, wherein the targeted user whose accelerometer is exploited by the attacker is in call with the remote caller. So in this situation, the targeted user places the remote caller on the loudspeaker while still talking to the remote caller. So when remote caller speech is generated via the targeted user's smartphone's loudspeaker, those speech vibrations are picked up by the accelerometer on the targeted user smartphone, and thereby picked up by the attacker, who can then use it to exploit the speech privacy and lead to a leakage of the private conversation. Next, we have the speech media privacy exploit, wherein the targeted user is playing as any media, such as music or YouTube clips or personal videos on their phones, but at the same time using the onboard loudspeaker. In this case, the onboard loudspeaker will generate speech vibrations. Those are, again, picked up by the onboard accelerometer, and which are later then leaked to the attacker. The third scenario in this exploit is the voice assistant response exploit, wherein a user might issue a command to a voice assistant present on the smartphone, and the smartphone might reply back with the response to the user's query. In this scenario, both the user command might be replayed by the assistant, followed by the query, and if both are using onboard loudspeaker, the command and its corresponding answer would generate vibrations, which would be picked up by the accelerometer and transferred to the attacker, wherein the attacker can learn the command and the response of the voice assistant. To design our Spearphone attack, we logged accelerometer output while the targeted speech is being played at the same time. To identify and extract the speech areas from the sensor output, we used a sliding window on the power spectrum of the speech output from the sensor. We used the shortest word length to specify the size of the sliding window. Anyway, we measured the boundaries of speech using power variance within the sliding window. After selecting the speech areas, we performed gender, speaker, or speech classification. To perform these classification acts, we needed appropriate feature set that could capture necessary information. We tested standard classification algorithms listed here, and we found out that the random forest outperforms all the other classification algorithms. There were some challenges that we faced during its Spearphone's design. The first such challenge was limited sampling rate of the accelerometer. And operating systems like Android limit the sampling rate of motion sensors to prevent battery drainage and to preserve the computational resources. This leads to incomplete speech reconstruction, because complete speech reconstruction is not possible with low fidelity sensor data, because we don't have enough data in the output. Hence, we restrict ourselves to word isolation using root mean square of the power spectrum and keyword search, which uses a finite dictionary to look for certain words. In our scenario, we only look for credit card numbers, social security numbers, names, and other things. Another challenge was to pick up the appropriate feature set for accurate classification. The most commonly used feature sets are MFCC and time frequency feature sets. We found out that the time frequency feature sets outperformed the MEL frequency separate coefficient feature set. We'll now list the results of our experiments. First, we perform gender and speaker classification for voice call. We use both tenfold cross-validation and test and train methodology on two datasets, TI digit dataset, which contains digits from 0 to 9, and PGP word dataset, which contains PGP words uttered by 10 speakers. As we can see here, across the tested smartphones, Galaxy S8, Galaxy S6, Note 4, and LG G3, both gender and speaker classifications have a significant degree of accuracy for our attack. Gender classification has a bit higher accuracy than speaker classification because in gender we only considered male and female gender classification, whereas for speaker classification we had 10 speaker classes. These are results corresponding to the surface setup, which you can recall was where you place the smartphone on a hard surface. In the handheld setup, as you can see, the accuracy is dropped a little bit, which might be due to unintentional user movement while holding up the phone. We also considered loudness of the speaker while generating these speech vibrations, because the strength of speech vibrations is directly related to how loud the loudspeakers are. As you can see here, even at 75% of the maximum volume, the gender and speaker classification results for the two data sets were very significant when compared to a random attack. There were other considerations, such as in surface setup, would the accuracy change between soft surface and hard surface? As you can see, for gender classification that we tested on, it was like 87.5% for soft surface, which is lower than a hard surface like wood, but still it's similar to the handheld setup. We also considered natural speed data set that contained some noise, and it wasn't just a word data set as our tested data sets, but complete sentences. As you can see here, the speaker classification accuracy was similar to our previous single word data set. We tried to generate realistic voice call scenarios by downgrading the PGP word data set to 8 kilohertz. There was a decrease in both gender and speaker classification, as you can see here, which was expected, because if you downgrade the sampling rate, you are eroding the information contained in the sample. Next, we perform speech recognition in voice calls, two scenarios: single speaker, where you either recognize the speaker or the speaker is unknown. So it's a binary classification, and we have multiple speakers, where we have multiple speakers in a conference call, for example. In our experiment, we used 2 speakers, one male and one female. As you can see, for single speakers and multiple speakers, the both tenfold cross-validation and test and train methodology on our dataset revealed significant accuracy of our attack. For multimedia and voice assistant threat scenarios, we used Vox Celeb dataset for multimedia, which contains YouTube clips from interviews from famous celebrities. And the speech recognition accuracy here was 0.35 or 35%. For a random attacker, it would be it's significantly higher than a random attack. For PGP word dataset for voice assistant, we chose Alexa by Amazon as the voice assistant, and used our PGP word dataset to regenerate the words in Alexa's voice. The speech recognition accuracy was 0.31, which was again higher than the random attack. For speech reconstruction, as mentioned earlier, we were restricted to word isolation, and which uses root mean square of power spectrum and locates local peaks and values to identify words. We had 80% success rate in isolation of individual words. And once we have isolated individual words, we could do a keyword search using a pre-constructed training model. And for each keyword, we use prediction probability as confidence level. And then we can establish a threshold to indicate whether we accept a particular word as a given keyword or not. There are some limitations to our work. Our attacks and the threat scenarios might not always be practical. As mentioned, loudspeaker volume varies with user and phone models. We have very limited data set, which is useful for identifying keywords, but not so much for full reconstruction. And hand movement of the user, hardware design, and current improvements in both accelerometer and the loudspeakers affect the accuracy of our attack. Some countermeasures could be having strict access control policies around motion sensors, so that the user just doesn't blindly grant access to any app for motion sensor usage. We could also filter out speech frequencies for motion sensor data, and also insulate the motion sensor data against speech vibrations, so that these vibrations are absorbed and do not affect the motion sensor output. Comparing with previous works, the Usenix works that considered gyroscope to pick up speech vibrations from a nearby external loudspeaker. They had significant gender classification and speaker classification accuracies, but the difference is that our work considers an onboard loudspeaker instead of an external loudspeaker. And when we use onboard loudspeaker, of course, we have improved accuracy. There was another similar work which was done that used deep learning for classification and had a speaker recognition accuracy of 70% for 20 speakers. In our work, we show better accuracy with lightweight classification algorithms. We do not use deep learning, but restrict ourselves to off-the-shelf machine learning tools like Weka, Workbench, and use standard machine learning algorithms. That would be all. Thank you. I will now take questions.
Mentioned before we started the presentations, we're going to have all three talks first, and then we're going to have our presentations at the end. In the meantime, though, please do put your questions in Slack. I'm going to queue those up, and then we'll get to have the presenters opportunities to answer those questions at the end. Our next talk is going to be from Shengye Wan from William & Mary, along with his co-authors from George Mason and Washington University in St. Louis. And this paper is looking at mobile device management, MDM, which you've probably heard of before. But what happens if the operating system is compromised, and what does that do to the guarantees you get? And so this paper is looking at how we move that functionality into TrustZone so we can have more assurances that these policies are actually going to be enforced. So with that, let's start the presentation.
Hello, everyone. Thank you for watching this talk. My name is Shengye Wan. I'm a PhD graduate from the College of William & Mary. This paper collaborated with Professor Sun from George Mason University, Professor Zhang from Washington University in St. Louis, and Dr. Li from my college, William & Mary. In summary, our paper presents a study which improves the security of mobile device for receiving remote commands, and we take advantage of ARM TrustZone technology to build our system. Here is the outline of today's presentation. I will first introduce the motivation and background of our work. Then I will give an overview of our work and present our main contributions. Later, I will present the implementation and evaluation of the system. And finally, I will conclude our work as several takeaways. First, let me introduce what motivated us to design this work and some background knowledge. In recent years, mobile devices have become an essential part of the corporate and government employees, and therefore, mobile devices get more chances to process and store sensitive information. For these devices, it is important to guarantee that a remote administrator can perform critical operations on mobile, such as providing the remote support and a security patch. These remote operations are called as mobile device management, or MDM. Nowadays, more and more vendors are providing their MDM solutions, including Apple, IBM, Microsoft, and Verizon. A typical MDM workflow would involve three basic components. The remote administrator sits on the server side, the MDM agent sits on the mobile side, and the management commands connect both sides. Since many MDM agents perform security-related tasks, these agents are highly sensitive about their security. Currently, most MDM agents are deployed with a rich OS like Android, so a compromised rich OS may disable all MDM service at once. Meanwhile, in 2020, we see more than 800 new CVEs are reported for Android, which suggests that a security-sensitive agent should get implemented somewhere safer, and that place on mobile is ARM TrustZone. As our work's background, ARM TrustZone technology can isolate all system resources, such as the CPU and the memory, into two domains. The first domain, called normal world, is used to support daily applications and a rich OS like Android. Meanwhile, the secure world works as an isolated environment, and it only serves for the security tasks. Under the ARM TrustZone threat model, the entire normal world is untrusted, including the rich OS. Meanwhile, by taking advantage of the hardware-assisted isolation, all the threats are believed to be restricted inside the normal world only, so the secure world software are safe from the normal world attackers. Therefore, the secure world is an ideal place to deploy our security-sensitive MDM agents. Though there are many security benefits of TrustZone Secure World, there is also a major challenge to use Secure World to support MDM, which is how to provide a network security. With TrustZone architecture, the most straightforward design is to allow the secure world on its exclusive network hardware, so the normal world cannot interrupt any receive or transmit data about the secure world side. However, due to the limited hardware space on mobile, Most mobile devices only equipped with one set of network device, which means the mobile needs the normal world and the secure world to share the network device, no matter it's a SIM card or Wi-Fi controller. Therefore, in this work, we are trying to answer the question that, when sharing the NIC, how to provide a reliable network for the secure world. In the following presentation, I'll use the term NIC to represent all kinds of network devices. As the last part of our background, let's quickly go over the workflow of a NIC with its associated driver. Here we assume the NIC is enabled with the DMA feature, which means the NIC can directly access the memory to handle the network traffic. To work with the NIC, the network driver will first allocate some data structures, including the driver's software interface and packet buffers. The interface is responsible for saving the detailed information of packet buffers, such as the buffer's address and size. Meanwhile, the packet buffers are used to save the real network packets. With such a design, the NIC and the driver can read and update the interface to work collaboratively and asynchronously. Now assume one packet arrives on the NIC. The NIC would locate the interface according to some registers on NIC, and then the NIC can extract all the information from the interface and finally save the packet in the buffer. Now I'll present how does our work make the two worlds of ARM TrustZone to reliably share the same NIC, and what's our major research contributions. Intuitively, there are three design options for sharing the NIC. The first option is using one network driver in the normal world to serve both worlds together. As nothing changes on the normal world rich OS, this option is the best for the normal world performance. Meanwhile, this design gives the normal world fully control on the secure world network. If we consider the previous workflow, we can see that under TrustZone threat model, all the involved data structures and the entire driver can be controlled by the attacker. So this option is unreliable from the security perspective. The second option is deploying the only driver in the secure world, so the secure world can trust the driver and any other related data. However, since normal world cannot access the secure world memory, any normal world software cannot directly interact with their network packets. And in this case, the secure world is required to frequently forward all normal world packets back to the rich OS or the upon applications. And this forwarding incurs a large overhead on the normal world side. Finally, we may deploy two drivers in two worlds separately and allow each world to have their independent interface. This sounds reasonable, while for a typical NIC, at any time the hardware piece can only connect with one set of software interface. So it is still challenging to decide when should the NIC connect with the normal world interface and when should the NIC connect with the secure world. As we explained so far, all three intuitive solutions are not practical for some perspective. Now I'll introduce our solution, which we call TZ-NIC. In TZ-NIC, we deploy one complete network driver in the normal world and the other slim driver in the secure world. The normal world driver is allowed to initiate driver, which include connecting its interface with the NIC. Meanwhile, the secure world driver is responsible to securely reuse the normal world interface by using the secure world's high privilege to read and write on the corresponding register and memory. With such design, we can have two drivers running on two cores simultaneously by sharing this interface. With our TZ-NIC design, we will face two major challenges. The first one is that since the secure world driver cannot trust normal world driver, it needs to locate and use the interface without any normal world help. This is the semantic gap between the normal world and the secure world that we need to fill. Also, because both drivers are interacting with the same interface, we want to make sure that the secure driver can work under the interference of normal world driver or even the normal world attacker if there is one attacker here. Now let me first explain how does a secure world driver identify and reuse the interface. First, the secure world driver reads the NIC's registers to locate the normal world interface. With ARM TrustZone architecture, all registers are guaranteed to be readable to the secure world. Therefore, any normal world attacker cannot hide or fake these registers' values. Second, since the interface and the buffers are saved in the normal world memory, ARM allows secure world to have enough permission to read all these memory areas. Therefore, our secure driver can get all the necessary information from the memory directly. Also, since every NIC hardware is designed to use the interface with a fixed format, Secure Word Driver is promised to understand the interface in memory. By putting all conditions together, the Secure Word Driver can finally find every network packet that's saved in the normal word memory correctly, and it does not ask for any assistance from the normal word side. To resist the interference of normal word, we propose two techniques. The first one is using the secure timer to activate our secure word component, and TrustZone technology can promise that no normal word attacker can interrupt with the wake up of our mechanism. After the wake up, the secure word driver will read all receiving packets in parallel of the normal word driver. Moreover, we propose the secure word to work with a loss-tolerant packet, such as the UDP packet. Therefore, once TZNIC detects any packet for the secure word, it can save the packet in the secure memory as soon as possible, and the attacker cannot delete them afterwards. Now, I will present some details about our implementation and evaluation. We developed a TZNIC prototype on the ARM development board Juno, and the board uses a Marvel Yukon 2 NIC with the open source network driver Sky2. Assume a manufacturer wants to migrate the Sky2 driver in the secure word without our prototype. Then he or she needs to migrate the entire 5,700 lines of code into the secure word. Meanwhile, as the comparison, our prototype deploys the Steam version driver with only around 1,000 lines. As for the evaluation, I will focus on presenting the reliability of TZNIC today, and you can find more evaluation about the system performance in our paper. To evaluate the reception reliability, we first deploy an attacker with kernel page on the normal word, and we use this attacker to keep deleting the packets from the driver's packet buffer directly. To demonstrate the baseline capability of our work, we test the attacker with a network benchmark iPerf, and our attack can fully block iPerf from receiving any packet. Meanwhile, when facing the same attacker, we test 100 rounds for the TZNIC, and our prototype can receive 67% of the packets on average, with the minimum receiving rate as the 22% and the maximum rate as the 92%. Finally, I'm going to conclude this work. So for you to take away today, our work makes TrustZone Secure Word become a good place to protect MDM agents or other softwares that require reliable network service. Specifically, by adopting TZNIC, even when the two words are sharing a hardware device, we can make the secure driver to reuse part of the normal driver data structure because the secure word has higher privilege to inspect the data and get execution. Finally, the entire process of TZNIC has no requirement on the normal word, so it's totally transparent to the RichOS and Apple applications. That's all for my presentation today. Now we can discuss if you have any question or suggestion on our work. Thank you.
Thank you, Shengye. And a reminder, we're going to have all of our questions after the three presentations, but please do start typing your questions into Slack so we have them there. Our third and final presentation of today is going to be presented by Jasper Stang, which is a paper along with his collaborators at University of Würzburg and Kolb Systems. And so this paper is going to be looking at the problem of task hijacking in Androids. This is the idea that you can overlay new screens on top of what you're doing, and you can confuse the user to enter information into the wrong application. And this paper is going to be looking at novel approaches to detecting those sorts of attacks. Let's start the video.
Hello everyone, my name is Jasper Stang, and today I'm talking about the StrandHogg attacks. I hope you already know them, but if you don't, I'm going to explain them later. I'd like to start with the problem statement. It's all about the StrandHogg attacks, which threaten the security and privacy of up to 2.7 billion Android users worldwide. There are actually two versions of the attack. The first version affects Android versions 4.4 to Android 10. And according to the worldwide Android version market share 2020, around 99% of devices are vulnerable to this version. It is not fixed with any patch, and therefore those devices will remain vulnerable. The second version was fixed using a security patch, and the vulnerable versions are 4.4 to 9.0. That corresponds to roughly 75% of devices worldwide. However, we face the problem that around 20% of devices will never receive a security patch for the second version because the vendors no longer support the devices. That leaves them vulnerable to the attack, and other mitigation strategies have to be employed. I want to talk about the concept of StrandHogg now. The attack belongs to the class of UI deception attacks. First, I want to start with some Android background. In Android, you can create activities which are the main element for user interaction. All activities are kept in a task, and each task belongs to a certain app. As you can see in the figure, we have one victim app with a task, and each task can have multiple activities. Now, let's take a look at a malicious app. The basic principle of the StrandHogg attacks is to inject a malicious activity into the task of a foreign app. As you can see, the malicious activity still belongs to task 2. However, in Android, you can specify the task affinity attribute, which controls the belonging to tasks. In this case, we change it to task 1, and therefore the malicious activity will be injected into the task of the victim app. This has severe consequences, as it enables, for instance, highly sophisticated phishing attacks, which can be used to steal security-sensitive input, such as passwords. The second version of the StrandHogg attack achieves the task injection without modifying the task affinity attribute, but it works very similar. Let's take a look at the mitigation of StrandHogg attacks now. We have 3 types of mitigation methods here. The first one is static analysis. It works by inspecting the task affinity attribute and therefore detect apps that try to exploit the first version of the StrandHogg vulnerability. The second type is runtime detection. It analyzes, for instance, activity transitions and tries to detect malicious patterns there. It can be used to detect both types of StrandHogg attacks. However, it is implemented by modifying the operating system. The last type is enforcement of attributes. This method modifies the launch mode attribute of apps, which prevents both StrandHogg attacks. However, this approach has severe usability drawbacks, such as the prevention of multitasking, which is a critical feature for Android devices. Let's take a look at the overview table. I've previously told you that 20% of devices will not receive a security patch as they are no longer supported by the vendor. Therefore, defense methods relying on operating system modification cannot be deployed. All other methods have certain drawbacks, such as not detecting all attack versions or limiting the usability of the device. Therefore, no proposed solution satisfies all requirements. I'll now talk about our contributions. First, we implemented the StrandHogg attacks to gain an understanding of attack mechanics, and additionally we provide the source code for the attacks, which can be used to, for instance, evaluate defense techniques. We then developed our first detection method, which is based on machine learning. It can detect both StrandHogg attacks by classifying execution traces of the app. The last method is the activity counter detection method. It works by supervising the amount of activities in the app's task. Both methods are implemented by app providers into potentially vulnerable apps. That means they can be employed vendor independently on any device. I focus on the detection methods in this talk. Let's take a look at our first approach, the machine learning detection method. The basic idea is to collect traces with and without an ongoing attack and classify them into malicious or benign using machine learning models. The approach is actually split into 2 phases, and we'll consider the training phase first. We've implemented a data collection framework using a data collector app. This app collected traces which were stored on a server. The actual trace collection was done on multiple devices from different vendors with versions from 4.2 to Android 10, and during the collection of traces, normal app usage was simulated. The data collector app then collected attributes from its tasks, received intents and lifecycle events. We then did the trace collection again, but this time where one of the 2 attack variants was executed. The attacks targeted our data collector app, and we introduced 2 scenarios here. The first one is that the data collector is minimized, and the second one is that the data collector is closed. Our complete dataset contains around 900 benign traces, 580 that were collected during the first StrandHogg attack with minimized data collector, 240 with closed data collector, and 200 while the second StrandHogg attack was executed. Due to the nature of the second attack, it is not possible to collect traces with a closed data collector. We've then used those traces to train a machine learning model. In particular, we used random forest and the XGBoost classifier. And once the model training is finished, the approach switches to deployment phase. Here, we distribute the trained model to the devices and classify traces that were collected locally. And the result of our on-device classification then tells us if a StrandHogg attack is currently going on. I now present the results for this approach. First, I want to talk about the feature importance distribution of our XGBoost classifier. This is a convenient benefit of using decision tree-based models. As you can see in the table below, the feature num activities is contributing the most to dividing the data. And if you take a look at the Android documentation, it states that it represents the number of activities in this task. However, this doesn't really tell us much about the exact behavior of this attribute. We then engineered another feature based on the num activities attribute. It is called global num activities, and it is set to 1 in case the trace shows at least one occurrence where num activities is greater 1. As you can see, it almost had a 3 times higher importance than the original feature. We then performed binary classification on the traces into benign and malicious and achieved an accuracy of up to 95%. However, as you can see in the bar chart on the right-hand side, the accuracy significantly drops for the first StrandHogg attack version, where the data collector is in a closed state. And this observation actually led to further investigation of the num activities attribute. So, while investigating this attribute, we could make some interesting observations, which led to the development of our second approach, the activity counter. We already know from the previous approach that the num activities attribute is a reliable attack indicator for the second StrandHogg attack and for the first StrandHogg attack in case the data collector is minimized. Let's now take a closer look at the behavior of this attribute. Consider a main activity in a task. If we query the num activities attribute of this task, we'll get 1 as a result. If we close the main activity, the amount of activities is actually 0. However, the num activities attribute will still report 1. And in case a malicious activity is now injected into the task, the num activities attribute will again remain at the value 1. But if we add the main activity to the task again, then the reported value is 2. And that's how we can detect ongoing attacks. So the strategy for attack detection is as follows. We compare the num activities attribute with the amount of our own created activities, and in order to reliably detect attacks, we need to keep the monitoring app in a minimized state, because in this case there's always at least one activity present in the task. We have to solve 2 challenges to make the activity counter feasible. The first one is that we need to prevent the closing of the monitoring app, as our attack indicator is only working reliably in case at least one activity is present in the task. The solution to this challenge is to launch the main activity with the flag exclude from recents as soon as the app is closing. After launching the activity, we instantly minimize it by calling the move task to back method. Let's take a look at it in the figure. We have a main activity that is closing, and we then instantly launch it again with the flag exclude from recents and minimize it by calling move task to back method. This minimized activity won't be displayed in the recents apps list due to the flag we set. This is very convenient as it doesn't confuse users this way. We observed that this minimized activity is sufficient to increase the num activities attribute by 1. The second challenge is to enable efficient monitoring. As of right now, continuous background monitoring is still necessary to detect ongoing attacks. We now take a closer look at the minimized activity that we placed in case the app was closing. The behavior that we observe here is that the onCreate method of our activity will be called regardless of the foreground activity of our task. Therefore, we have a callback in case our app's icon is clicked, which enables us to get rid of the constant monitoring component. As we've solved the challenges, we can now proceed with the concept of the activity counter. In case the device is started or the app gets closed, we place an activity with the flag exclude from recents. Now that we've placed our minimized activity, we can take a look at what happens in case the app's icon is clicked. Let's consider an ongoing StrandHogg attack. In this case, a malicious activity will be injected into the task, and the malicious activity will be the foreground activity of our task. However, the onCreate method of our minimized activity is still called by the Android system. We then evaluate the num activities attribute, and we know that we've only one activity that was intentionally created. However, the task will report 2 activities, and that's how we detect the attack. We have only one case to consider left, which is when the app is intentionally minimized by the user. In this case, we start a foreground service and periodically evaluate the num activities attribute. We can use a very low frequency for the periodic check of around 2 seconds. That's because our experiments that we've conducted have shown that this value is sufficient to detect all ongoing attacks. In case the app is resumed by the user, we can just stop the foreground service. Let me conclude the presentation. We first developed a machine learning-based approach. It detects both attack versions with an F1 score of 92%. The approach suffers from false positives and negatives, which has a negative usability impact. However, the approach was indispensable in order to understand the behavior of the num activities attribute. This attribute was then used for our second approach, the activity counter. It can be used to protect all vulnerable Android versions from both StrandHogg variations. It is a deterministic attack detection, hence it doesn't suffer from false positives or negatives. The periodic check that we employ is only necessary during phases where the app is minimized by the user. That means most of the time the resource overhead of the activity counter is negligible. Most importantly, it doesn't rely on modification of the operating system and can therefore be employed vendor independently on any device. Thank you very much for your attention.
All right. Thank you for the great talks to all three authors. Now we're moving into the Q&A part of the session. We're going to be doing 5 minutes for each of the presentations. Each of these in turn, the authors can turn on their video so that they can participate in the discussion. So the first paper we're going to talk about, the Spearphone paper, to have some Q&A here. I'm going to get us started here with kind of a high-level question. And so I don't know if you've seen some of the changes that are being proposed to being added into Android 12. And one of the things that I thought was interesting is they're going to be limiting the rate that you can query the accelerometer, so basically the granularity of information. And I was curious, one, if you were aware of that, and two, if you had any, even if not, if you had any thoughts on how that may impact your attack.
So when you say they're going to limit the granularity of the sensor outputs, basically like limiting the sampling rate further, or?
Yeah. So I was looking at this, and so there is a new permission for high sampling rate sensors. I'm thinking this may also work for accelerometer. It might just be some of the other ones, but I guess the high level question is here: how tied are you to the sampling rate, and do you think that a lower sampling rate would prevent this sort of attack?
Yeah, so this is like inherently based on the sampling rates themselves. Although what we have seen in the current landscape of Android phones is that from like, I would say like 2012 till 2020, the sampling rate has been increasing further and further. Like the phones that were in 2016, like the ones that we used in the very early stages of our experiment, LG-G3 was around, it was less than 200 Hertz. And then the Samsung phones like Galaxy S6, they were a bit over 200, they were like 250. And then Samsung Galaxy S8 was around 400 Hertz. So because, the many modern phone manufacturers tend to increase the sampling rate to improve on the data that they collect. And that helps with our attack. But now if we are reversing the course and we are like, again, putting restrictions on the sampling rate by the OS, then that would definitely make the attack less accurate. But as we have also tested LG-G3, which had like 200 Hertz, and that still works. So and the other thing is that for every sampling rate restriction, you're going to suffer, the data quality will suffer for that sensor. So it's a balancing act. And what we have shown is that from like till 2000 Hertz, the attack would still be a threat. Now, if you go below that and use some other mechanism to boost the data output, we'll have to revisit this whole attack scenario.
That might be an interesting follow-on work. I put a link in Slack to the Android page talking about. There's not a whole lot of detail there, but it might give cause for new algorithms to see if that attack is still possible given these limitations.
Sure. Yeah.
There's a question from Slack. This is from Merturza. And before I ask the question, Merturza, would you like to ask the question yourself? I take silence as a no on that. Oh, he's typing.
Yeah. So
says go ahead. So the question is, how is the attack expected to perform in a realistic setting in the presence of noise, specifically when the target is moving, that may directly impact the accelerometer readings? Would the attack work better if data from gyroscope is supplemented with the accelerometer data? And he thinks that you had a great talk and it was very interesting work.
Thank you, Murtaza. And that's a great question. Any attack that we are proposing in the field of security, there should always be a talk about how realistic the attack is. So let's this attack is, as you can see, it considers 3 threat scenarios, and I would say they're pretty realistic. But again, the experiments were conducted in a lab environment, and especially like threat instances where we are eavesdropping on the remote caller speech privacy, they can be a bit dicey in realistic scenarios, especially like when the attacker knows that the remote caller is on speaker, and how to label the training data and all that sort of things. So there's always some caveats for these attacks that are done in lab settings. For the presence of noise, specifically when the target is moving, so the user mobility interference, that can be filtered out if we use a high-pass filter to filter out all the frequencies that are below 2 Hertz. And this figure is coming from previous work that was done and presented in Mobisys. I think it's called Accelerometer, and they used the same time frequency features that we used, and they found out that so the threshold is at 2 Hertz. If you filter out frequencies that are more than 2 Hertz, then we are interfering with our classification accuracies. So I would say that we can minimize the mobility interference by using a high-pass filter. Would the attack work better if data from gyroscope is supplemented? It should in theory, but then we have to consider how much data gyroscope is picking from the speech, right? So I think in the gyrophone paper by Miklevsky, that was in SNP 2014, I guess, they used gyroscope as microphones, but they were using external loudspeakers that are much more powerful than the onboard loudspeakers. So again, it's a future avenue for this work. And if we can see that gyroscope does pick up a significant amount of information from the speech vibrations, then definitely we should look at sensor fusion here.
Great, thank you. And so let's thank Abhishek again, and so let's move on to our next paper. Shengye, if you can turn on your video.
I already turned on.
Oh, there it is. It didn't pop up for me. I just had to speak. All right. So let's start in Slack here with the questions. Merturza again is asking, says, great talk. Is it possible for an attacker to selectively compromise the memory and memory map of the normal world to trick and mislead the secure world driver?
Yeah, thank you for the question. I think our paper, most defense is based on this manipulating the normal world memory. So yeah, we do definitely assume the attacker can manipulate any normal world memory. And our work actually split into 2 parts. The first part is we are filling the semantic gap, which means we are trying to locate all these network interface. And with that part, we are basically just based on the normal registers, as I mentioned, on the NIC. So as long as the NIC is still running, there's nothing the attacker can manipulate. And the second part, we need to move the network packet from normal world to the secure world. So for this part, the attacker really can like feed some false packet in that case. And our paper have mentioned a special section about how to defend this feed like for fake packets. Like we use the incremental ID and we use the encryption, but there are some typical techniques, so I don't mention in my presentation. So I hope this answers the question.
I had a somewhat related question. So you're relying on the scheduling algorithm within TrustZone to trap you back into the secure world to do some of these checks. And since this happens at an interval, the first thing I'm wondering about are there different race conditions that can occur? And I don't have anything specific in mind, but what are the sort of potentials for race conditions to impact either some sort of denial of service or guarantees in other ways that you're trying to provide?
Yeah, that's a good question. So fundamentally, I think that the baseline is like we assume the NIC is not fully disabled. Like if the phone is totally offline, or like if you plug off the NIC, then our cannot work. And besides that, since we are using the secure timer to periodically, or we even consider to use some random wake up mechanism. So in that case, the most risk condition is come from like you have one core running normal world and you have one core running secure world. So that's the basic model. And in that case, the attacker can try to delete the packet while we are reading them. So there is a risk condition. And meanwhile, based on our testing so far, like we can still win the risk condition in some circumstances. Like our rate is averagely 67%, I believe. So we believe as long as we have every network packet as the loss tolerant case, then as long as we can capture like one of fifth packet, then we are good enough to understand what's the command recently.
Great, thank you. I don't see any other questions in Slack. Another question I had was one of the things you were saying that you don't have to change the host OS at all. And it wasn't entirely clear to me how generic you are, right? So if this is something coming over cellular radio versus coming over Wi-Fi, how are you able to be so generic in that way?
Yeah, so when we mentioned we are not modify any rich OS file, we still have some work to adapt to every model. And that work is like we have to understand how does the NIC and that hardware interface like collaborate with the driver. So like in our case, we understand like on the NIC register, which register specifically tell us like what's the normal world physical address to retrieve the first layer interface, and then we have to understand the NIC's interface to further retrieve every network packet. So it's not like we can generically, like magically, no effort to apply to any hardware model, but as long as we can understand how the hardware piece collaborate with their driver, we can re-implement the similar like methodology in the secure world to retrieve all these things. But yeah, we really do not need to like interfere the rich OS in that case. Just let their driver run in their original way.
Yeah, I guess my question was more along the differences between maybe a Wi-Fi driver and the interface to the radio, because the interface to the radio goes through a separate daemon, and that's controlled by the baseband.
Oh, I see. Yeah, I think as long as it's the DMA based, so the secure driver, like architecture-wise, they are assigned with all this privilege to read all this register and memory. So as well as the secure world has the privilege to read the first layer register, and we can touch that memory space, I believe we have the enough privilege to retrieve. But yeah, I personally do not test with any baseband yet, so that's a good question. I think we can consider some kind of future work.
Sounds great. All right, well, thank you again. And let's transition to our third presenter, Jasper. Jasper, if you can turn on your video.
Yes,
it's not already
I'm
on.
here. Can you hear me?
Yep.
Yes.
I can hear you and see you now. Wonderful. So why don't we start with the questions in Slack? And so, Teresa, again, fantastic work, and thank you for the great talk. It's asking, what was the test validation set used for the results in your ML-based detector? Was cross-validation done? If yes, what was the training validation split?
Well, thank you. We've used a train test split of 75 to 25%. So we've randomly selected 75% of the traces and used them as training set. And for validation, we chose the remaining 25%. As far as I remember, the cross-validation is not included in the paper, but in our experiments, we've used tenfold validation, and the accuracy results were pretty similar here.
And then he also has a related question in terms of the performance impact of the activity counter-based approach.
We haven't actually measured the performance impact of the activity counter. However, due to the callback that we've placed, so the onCreate method, we can get rid of the continuous background monitoring most of the time. So the only case where the performance is actually impacted is when the app is intentionally minimized by the user. And as I've said in the presentation, we can use a very low frequency for our periodic check here of around 2 seconds. So that shouldn't have a very high performance impact. And for the actual counting part of activities, this doesn't really have any impact at all. It's just increasing a counter or, well, decrementing the counter.
Great. So I had originally I had a question where it wasn't clear to me whether or not what you're proposing was a separate app that got installed and was monitoring, or if this was something that developers were adding into their apps. And it sounds like it's a separate app you could install to help protect your phone. Is that correct?
No, actually, it's not. So each app that wants to be protected or that desires to be protected has to integrate our solution. So basically, each app that is security sensitive should integrate this activity counter solution into the app.
So there have been some APIs that Android has provided over the years to prevent these sorts of attacks. Have you looked at all the adoption of applications and using those available APIs?
Can you specify the API?
So there are ways like that you can turn off screen capture, or basically so that if you're basically blanking the screen if you go to the home window, various sort of screen capture attacks and different sorts of sort of hardening things that developers can do if their screen is sensitive in some way. And I forget if anyone's done any studies looking at the adoption of those techniques and wondering how your approaches, for example, might be able to help in those scenarios, or will they adopt your approach? What can you do to help them adopt?
I'm not really sure if I got the question correctly, but
so I guess what is how can developers be encouraged to adopt these approaches? I guess how do you get people to adopt them once you've put them out there?
I think because they are easy to implement and enhance the security of their apps. So
is this something that you can? So I guess what I'm thinking about is some of those APIs you've got to call APIs, right? You've got to do that. Is this something where you can just, here's a jar file, add this into your package, and all of a sudden you're protected, or is there more to do than that?
There's a little bit more to it, but it's not that complicated. So I'm pretty sure that based on our work, someone can well, develop a framework or something similar or a library where you can have a a solution that can be really easily integrated into any existing app. So I'm confident that future work will solve this issue. As of right now, you have to have some minor changes in your code base to implement the solution.
All right. Well, I don't see any additional questions in Slack, and we're right at time. Let's thank Jasper and the other authors. And that concludes this session. We're now moving on to a 30-minute break. So we'll see you back here in half an hour. Thank you.
Okay, I will make a quick short announcement before the break. So first and for all, thank you, Will, for chairing the session. And also a big thank you for the authors for their presentations. So as Will mentioned, we will now have a break of 30 minutes. But during this break, we're also going to show short 1 to 2 minute interviews of each submitted demo and poster. So I recommend that you do take a break, please walk around, stretch your legs, get something to drink. But meanwhile, you can keep the audio of your Zoom or YouTube stream on, so you can also listen to these interviews. And the actual demo and poster session will take place tomorrow on GatherTown. So that concludes this quick announcement. So enjoy your break and enjoy the interviews.
Hey, I'm here with Alex. Alex, what will you show us in the poster and demo session?
I will demonstrate OpenHaystack. OpenHaystack is a project which uses the Apple Find My network to find lost iPhones and MacBooks normally, but now we opened it up to enable it to find any Bluetooth device that you have. So OpenHaystack is a macOS application, and it also contains several firmwares for Bluetooth hardware like the ESP32 or an NRF chipset.
Excellent. So what will the participants get to see during the session?
So we will demonstrate our Mac app and show how you can easily deploy your Bluetooth devices and find them later with the app. And also we demonstrate that you can even see the past history of your devices for the last 7 days. And then we give a short introduction on the Apple Find My network, how this works.
Cool. Can the participants also try something at home as well?
Yes, of course. All you need is a MacBook, and our code has been published on GitHub already. And we have created a community there with over 2,900 stars and several contributors to this project.
Excellent. So I'm looking forward to seeing you in the poster and demo session.
Thank you.
Hi, I'm here with Milan, who submitted a demo to the poster and demo session. What is your demo about?
So we have discovered severe privacy flaws in AirDrop, which is Apple's wireless file sharing service. And we described the original flaw in theory and presented a solution to the problem in our paper called Private Drop Service. We will present at Usenix Security this year. And this WiSec demo can be seen as an extension to our theory, where we wanted to show that the discovered flaws are easily exploitable in practice.
So as an Apple user, can I do something to prevent this from happening?
There's not really a lot you can do because this is the design issue of the protocol itself. So you're left with not using AirDrop at all.
That's unfortunate. So what will the audience get to see during the session?
In the session, we will demonstrate that an attacker can learn the phone number of nearby AirDrop users in a matter of milliseconds.
Great. And did you also publish the tools you're using for your project?
Yes, we put our proof of concept on GitHub.
Excellent, and I'm looking forward to seeing you in the poster and demo session.
Thank you, Eric.
Hi, I'm here with Haiping. So what did you submit to the poster and demo session?
So our submission is about deep learning-based radio fingerprinting. In this study, we improved the test accuracy of deep learning models in cross-state scenario by leveraging transfer learning, such as fine-tuning techniques.
Nice. So what is your main result there?
So we use transfer learning to improve the accuracy in cross-state scenario. Specifically, we train a deep learning model based on the IQ data we collect from day one. Then we fine-tune the pre-trained model based on the IQ data we collect from day two. And by doing so, we can improve the test accuracy to 76%. But without our approach, the accuracy is only around 29%.
So what can you show to the audience during the session?
So in our presentation, we will highlight the limitations of existing studies and explain our main ideas. And we will also explain how we set up our test band and present the details of our experiments.
Are the tools used for that available as well?
Yes, the tools are available on the GitHub, and also I will use a video to show how we run our tools, and also I will include the links to the GitHub.
Excellent. So I'm really looking forward to seeing you in the session.
Okay, thank you.
Hi, I'm here with Marco, who submitted a poster to the poster and demo session. What is your poster about?
So, hi Eric. We present an attacker-agnostic spoofing detection method for GNSS based on high-precision local flux. Highly integrated receivers are often provided with extensive connectivity that can be used to obtain network time. This option might not be available in case of coordinated attacker action. So we provide single or ensembled high-precision, often compensated oscillators on the GNSS receiver platform to cross-check the state of the GNSS clock against a precise reference.
So what is the main advantage of your solution?
The advantage of the solution is that it operates in a non-connected state for long periods of time. It can provide a precision reference directly at the GNSS receiver. It doesn't require specific connectivity to work, and potentially could provide even old over for the time solution from the GPS receiver once the attack is detected.
Excellent. Then I'm looking forward to seeing you in the poster and demo session.
Thank you very much.
Hi, I'm here with Sen Sun, who submitted a demo to our poster and demo session. What is your submission about?
Our Open Wi-Fi CSI fuzzer aims to offer more privacy protection to the Wi-Fi CSI sensing applications. With the CSI fuzzer, the passive or secret CSI sensing becomes impossible. We have built the feature into the Open Wi-Fi, which is an open source Wi-Fi chip. So the demo runs in the real world together with the smartphone.
Excellent. And what will the audience get to see during the session?
Basically, the Open Wi-Fi CSI fuzzer offers CSI manipulation capability at Wi-Fi transmitter. In this demo, we will set up the Open Wi-Fi AP and use a smartphone to access the internet via this AP. Meanwhile, the CSI fuzzer changes the CSI randomly in real time at the Open Wi-Fi transmitter. And we will also show the real-time random CSI by the Open Wi-Fi CSI extraction tool over the air.
Great. And all those tools, are they available as well?
Yes, we have published it under the Open Wi-Fi project. You can find our GitHub address easily by simply search Open Wi-Fi on internet. And CSI fuzzer can be found in the application notes section from the README.
Great. Then I'm looking forward to seeing you in the poster and demo session.
Also looking forward to all of you. Thank you.
Hi, I'm here with Malte. Malte, what did you submit to the poster and demo session?
Hello, we submitted the demonstration replay attack on GNSS signals. Spoofing attacks on GNSS signals can mislead victims with false location and time. We evaluate large distance replay attacks on GNSS signals with off-the-shelf hardware and consumer-grade internet. This simple attack type is not hindered by the introduction of navigation method authentication, such in Galileo, so additional detection schemes have to be implemented to protect the receivers. Unfortunately, as an end user, you cannot do very much, but the receivers will have to become active and implement a few of the many detection schemes suggested in literature.
Great. So what will we get to see during the session?
So the virtual format unfortunately limits us to showcasing the actual attack in a recorded video, but we walk the participant through the components the system consists of, the steps the attacker has to take to successfully spoof the victim, how the victim is then affected, and we also highlight the properties which can be useful to detect this attack.
Excellent. Then I'm looking forward to seeing you and your demonstration and all the other people you worked with in the poster and demo session.
Thank you. And we also look forward to see and discuss with you during WiSec.
Hi, I'm here with Nicolaisis. What is your poster for the session about?
It is about identifying wireless devices, Wi-Fi devices, by their unique pattern of the probe requests, in particular the timing of those probe requests across multiple channels. And the particular motivation for us was for an application for urban settings where we would like to know, for example, how many people are in a park. They're currently not associated with an access point, but we would like to be able to identify how many devices are there. And the first step is actually to identify the devices that presumably might be using micro-randomization and other techniques to conceal their identity.
That sounds like a great idea. So what can you show the participants?
What we will show is the exact types of timing information that's there in the probe requests and how they actually form bursts as well as transitions from channel to channel in sequences of probe requests and probe bursts, and how those are used as features to drive classifiers.
Excellent, and I'm really looking forward to seeing you in the poster and demo session.
See you there.
Hi, I'm here with Romain, who submitted a poster to our poster and demo session. What is your submission about?
This submission describes the implementation of a smartphone of a new kind of wireless attacks, named cross-technology pivoting attacks, and aiming at diverting a transceiver dedicated to a given wireless protocol to communicate with another one which is not natively supported, thanks to some similarities in their modulation schemes. So in this work, we focused on diverting the Bluetooth Low Energy stack of a Samsung Galaxy S20 to attack ZigBee and various proprietary protocols used by wireless keyboards and mices, such as Burst and Mozart. We reverse engineered the firmware of the Bluetooth controller, and we implemented our own transmission and reception primitives targeting these non-native protocols. It allowed us to perform multiple wireless attacks targeting keyboards, mices, and ZigBee nodes.
Great. Did you also publish your tools?
The source code is not published yet, but I plan to release both the firmware patches and the Android application during the poster session as open source software. It will be available on GitHub as soon as possible.
Excellent. And I'm looking forward to seeing you in the poster and demo session.
Thank you very much.
Hi, I'm here with Florent, who submitted a demo to our poster and demo session. What is your demo about?
Our demo is about a new approach of the firewall in Bluetooth Low Energy using a man-in-the-middle attack. So we place ourselves between the master and the slave in a Bluetooth Low Energy connection because it works with the master-slave paradigm. And then we are able to filter out some packets or some services from the slave. So we hide sensitive information from the slave or are able to filter out some specific packets in the connection.
Great. So what will the audience get to see during the session?
During the session, we will show the audience some video demos about real-life use of our tool on a smart outlet. So we will hide some services from the outlet and not allow the user to shut it down, for example. And we will also try to show some details on the implementation and how the tool works.
Great. And the tools you're using, are they publicly available as well?
Yes, the tools we're using are public and published on a GitHub repository.
Excellent. Then I'm looking forward to seeing you in the poster and demo session. Hi, I'm here with Jay, who submitted a poster to our poster and demo session. Jay, what is your poster about?
Hi, Eric. This poster is about a protocol called AgriAuth, which we have developed as a sensor collaboration and corroboration protocol for data confidence and security in smart farms.
Great. So what will the participants get to see during the session?
The participants will basically get an idea about how in future vertical and very connected farms can be compromised in terms of security related to sensor reports, sensor readings. So what we have designed is a protocol wherein we can identify any malicious readings based on the very basic principle that agricultural farms will have microclimatic conditions, and this will be reflected in code, very strongly correlated sensor readings. And we have developed a protocol which uses those correlated readings for authentication.
Excellent. So, and then I'm really looking forward to seeing you in the poster and demo session.
Thank you. Thank you, Eric.
Hello, I'm here with Domin, who submitted a demo to the poster and demo session. What is your demo about?
In our demonstration, we present a framework that allows researchers to more easily test and fuzz any Wi-Fi device. Users are able to write test cases, which can be used to test hypotheses on new weaknesses, implement proof of concepts, create testing suites, or simply automate experiments.
That sounds great. Did you also publish the tools you are using there?
Yes, the entire project is available on GitHub.
Excellent. And what will the audience get to see during the session?
In our demonstration, we will highlight the main features of our framework, followed by a demonstration which evaluates if a client station is vulnerable to the key reinstallation attacks, or not known as the crack attacks in Wi-Fi.
Excellent. Did you already get some nice results from your framework on real-world applications?
So far, we've been using this to test existing vulnerabilities and to create a test suite which can then automatically test for known vulnerabilities. But recently, this was also used by Mathy Vanhoef to create his fragmentation attacks in Wi-Fi.
Excellent. And I'm really looking forward to seeing you in the poster and demo session.
Thank you.
Mentens. I'm working at Leiden University and at KU Leuven. In this session on attestation, as I said, we will have 3 full papers that will be presented. And as you can see in the program, this session is scheduled for 1 hour. So we will first have the 3 presentations, of which 2 are pre-recorded, I think, and the last one will be live. And afterwards, we will go to the Q&A part of the session. So if you have questions, please post them in the Slack channel of this session, session 5. And you can use the thumbs up reaction to show which proposed questions you like the most, such that if we need to prioritize, we can do that. So let's jump to the first presentation, which is called FADIA, Fairness-Driven Collaborative Remote Attestation. It will be presented by Mohammad Mansouri. Mohammad is a PhD student at Eurocom. He's doing his research in the R&D department of Thales, and his PhD is on IoT security, covering remote attestation and network intrusion detection systems. So I hand over to the author or the video.
Hello, this is Mohammad Mansouri, a PhD student at Eurocom and Thales. I will be presenting FADIA, a fairness-driven remote attestation protocol. This work is a collaboration between Eurocom, Thales, KU Leuven, and University of Padua. So to start with, IoT devices are clearly now deployed in a large scale at industries. So these devices also are becoming a target for attacks due to many reasons that makes these are valuable targets. So we think of creating defense systems for IoT networks, and one way to do that is remote attestation. So we're going to give an overview of what is remote attestation and the main focus of this research, which we have 2 devices. One is verifier and the other is a prover. So the prover has some trusted execution environment inside it, and some applications are running in this prover. And then the verifier would like to attest, I'd like to prove, to verify the prover's software's integrity. And this will start by, at setup time, it will set up in the trusted execution environment some attestation code. This attestation code could be some checking on the hash of the firmware, or more complex stuffs like in checking the integrity of the execution path or something like this. And some secure key, which is only accessible by the trusted execution environment. And at step 1, it will send it a challenge. The verifier will send a challenge to the prover. The prover will forward this to its own trusted execution environment, and then the trusted execution environment will run the attestation code, or the attestation code will be run in the trusted execution environment to check the software integrity. And if everything is good and the prover is in a healthy state, then this attestation code will access the secure key and will solve the challenge, respond with the solution, forward the application of the prover will forward this to the verifier, and the verifier will verify this. Now, according to this description of the protocol, there are 3 areas of research. One is how to design a trusted execution environment in the provers. The second is how to build an attestation code algorithm to test the integrity of the prover software. And the third is how to manage this the communication between verifier and prover in order to achieve scalability for remote attestation. So this is the area of our research, the scalability of remote attestation. And this, for example, in a naive approach where everyone is attesting to the gateway was not scalable. And thus, in the literature, there are many solutions that have been proposed, mainly 2 types of solutions. One is gossip-based, where devices attest each other's in a neighbor, that they attest their neighbors, and they flood the attestations around so that everyone collects all the attestations. And then the gateway can access any device and collect the attestations of all the other devices from this device. In a tree structure form, another way to do collaborative remote attestation, devices may attest their children. So every child will send his prover, the device will attest to their parents, so that children will send the attestation to their parents. and the parents will do so for their own parents, and then the root device on the tree will collect an attestation that is an aggregation of all the attestation on the tree, which will be sent to the gateway, which will verify all the tree. Now, a hybrid approach has been proposed to create multiple trees and then create one token per tree to verify, to attest all the devices on the tree. And then we fluid out these tokens in order to achieve remote attestation for all the network. So we follow similar approach in which we do asynchronous multiple trees. So for one tree, the devices will create, find their children and send challenges and receives the attestation and the proofs from their children, but in an asynchronous way. So for example, if a device leaves, then if a device sends its proof, then it can leave. And then if another device attests, also it can leave. And this will happen gradually, so the device will be free, and there's no static requirement for a long time on the devices. And this happens for other devices, and also the gateway will receive asynchronously the proofs from different trees over time. So the first contribution in our design is considering a fairness, which is mainly targeting heterogeneity problem. So if in the heterogeneity problem, the device may have different capabilities. So we consider devices being more powerful than other ones and have more capacity than other ones. So we need a fair protocol for this. So let's take an example. For example, if you have this topology, let's say, which is equal opportunity topology, and you can see here like devices with 10% battery having the same number of children as the devices of 99% battery, which is an equal opportunity. But this is not fair. A more fair protocol would be something like that, which will preserve the battery for the 10% devices. And this can be also for devices for computational power, not only for battery level. To implement this, what we do is that we implement a score function. A score function is a function that is computed on the prover locally at time of attestation, and this will return from 0 to 1 a value according to the capability of the device, and this will be used to update some parameters such as the number of children this device can accept and the waiting time it needs to wait for until it participates in a tree. So as you can see here, how to interpret these results. For example, the number of children, if the score function is lower, then the number of children is lower, then you have less processing load and you have less forwarding of attestation. Similarly, for the waiting time, if you have less score function, then the devices have less time to attest, so they have to test in the beginning of the period of attestation, which means that they will finish the attestation earlier, and then they will go to an ideal state in which they do not listen to the network and save resources. Another contribution is that we consider devices being added to the network dynamically at runtime, which is a problem in typical networks because you have to reinitialize every other prover if you add a new device, because the keys that needs to be communicated with this device should be reinstalled on all the existing provers, which is not scalable. So we use an approach based on Echelon and Gligor. So this goes like this. There is a key pool offline which contains some keys. And then when a device wants to enter the network, it will go to this key pool and get some keys. This will be a random set of keys, which we call it key ring of prover 1. And then if a device prover 2 wants to enter to the network, then it will do the same thing and get some keys from the key pool. If there's any intersection between these two key rings of each prover, then they can use this intersection, this key, which is an intersection between both, for communication, for secure communication between them. Using this approach, we can perform collaborative remote attestation. Of course, there's not every prover is able to communicate with the other prover, but this is not needed for remote attestation as we build multiple trees. So sufficient connectivity around 60% is sufficient to create to run our protocol. So to evaluate this protocol, we evaluate it on 3 steps. 1, evaluate the benefits of fairness. 2nd, to evaluate its robustness against selfishness. selfish provers, and third is to evaluate it, comparing it to the state-of-the-art solutions. So first, let's start with the evaluation of fairness. So we consider a network with devices initialized with different battery levels. So we have 500 provers, and these provers will run for 11 hours, and they have to attest every 10 minutes. And we consider two variants of our protocol. One with a score function returning 0.5, representing not fair protocol, because it's always returning 0.5 regarding of the battery level, and another fair protocol which is returning the value proportional to the battery level. And according to this, we measure the time it takes until we see the first crash. I mean, crash means the energy of the first device is depleted. And we see this with different battery level distribution, and we can see that this fair protocol will conserve 10 times, or like an order of magnitude more time, lifetime, gives a lifetime to the network than an unfair protocol. Now we consider also selfish provers. So selfish prover is a prover that does not will to participate in a tree. So it does want to save its resources, and to do that, it will just send its proof to the verifier directly without participating in other trees, and move immediately to ideal state and not listen to the network. We increase the number of provers being selfish, and we again measure the lifetime of the protocol, and we see that for example, the dotted lines here are the unfair protocol, and the time at 0 is what we presented on the previous slide. And we can see that now the lifetime is decreasing until, like, for example, 50% of selfish provers, there is no more usefulness or advantage of using fair protocol. This showed that our protocol is robust to a certain level, but with a large number of selfish provers, it will be not useful anymore. Now we compare also to the state-of-the-art solutions, namely salad and pasta. For example, in terms of storage, we have a constant amount of storage independent of the number of provers, which is not the case for other protocols. And for example, if we take some numbers, we can see that they are our protocol is an order of magnitude less than other protocols in terms of storage per device. And then we also have we compared this our solution to pasta in terms of runtime. So for runtime, we can see that we can see here, for example, the colors representing topologies, static topologies. Namely, on the left are the three topologies, on the right are other topologies, and we run the protocol at the same time to see how much it takes for everyone to attest. And the dotted lines are for pasta, and the solid lines are for FADIA, our protocol. So we can see that in three topologies, like, they are pretty similar, and that's because of the bottleneck of the network delays. But on the right side, we can see, like, for example, for grid topologies, we can do much better. In summary, we have presented a protocol which is highly scalable, fairness-driven, and has a dynamic membership. It is still, this protocol is not autonomous, but this might be some area of research for future work. Thank you for listening, and I'm happy to receive questions.
Okay, thanks for the first presentation. So I'm reminding you of posting your questions in the Slack channel if you have any. Then we go to the second paper, which is on delegated attestation, scalable remote attestation of commodity CPS by blending proofs of execution with software attestation. And the presentation will be given by Ivan de Oliveira Nunes. Ivan is a PhD candidate at UC Irvine, and he will be joining the Rochester Institute of Technology as an assistant professor of computing security in fall 2021. And his research is on security and privacy, embedded systems, computer networking, applied cryptography, and especially at the intersection of all these topics. So please go ahead with the presentation.
Hello, everyone. My name is Vanhoef, and I'll be giving an overview of our paper Delegated Attestation, Scalable Remote Attestation of Commodity CPS by blending proofs of execution with software attestation. This paper is also co-authored by Mahmoud Amar, Bruno Crispo, myself, and Jean Sudik. And to understand what we're trying to do, first we need to discuss our setting, which is that of IoT devices, in particular, settings where you have several sensors and actuators that may be safety critical, may perform safety critical sensing and actuation, and these devices, they are under control of some central device, some home IoT gateway, home automation gateway, or some perhaps a main ECU in a car. And this device controls and relies on values that are sensed or actuation performed by several other lower end embedded devices, the sensors and actuators. And in these settings, one prominent approach to enforce security is called remote attestation, which is basically a method for remotely verifying the software state of one of these resource-constrained small sensors and actuators. And it basically, it's a way of measuring memory on these devices. The remote attestation protocol looks a lot like an authentication protocol, a challenge response-based authentication protocol, with one key difference. So as in an authentication protocol, this verifier would send a challenge to the prover, the verifier being some central controller in the IoT system, and the prover being a sensor or actuator that may or may not be compromised. And the prover is responsible for computing an integrity ensuring function over its own memory and the challenge. So in addition to authenticating itself, it also should authenticate the contents of its own memory. And then the verifier receives this response, and through the response, it is able to check whether or not the memory of the prover corresponds to the expected value, meaning that whether or not the prover is installed with the expected software. And this becomes challenging when we have to consider that the adversary may be in control of the prover, right? Because we're doing this to check if the prover is compromised or not. If the prover is compromised, then the adversary may be in control. The prover may try to lie or forge a response that will fool the verifier into believing that the correct software is installed when, in fact, something else is installed in the prover. So that's what makes this problem challenging and interesting. And over the years in this problem, there's a quite established taxonomy right now, which classifies remote attestation architectures in three types. There's hardware-based. So hardware-based typically relies on some standalone hardware module to allow implementing attestation, or some specialized CPU, specialized in terms of having a modified instruction set architecture just to enable secure remote attestation. And examples of that include trusted platform modules, TPMs, or Intel SGX, for instance. And they provide some strong guarantees. However, they are too complex and too expensive for the lowest end embedded systems that are used to implement sensors and actuators in these IoT settings. And then an alternative to that is what's called hybrid remote attestation, which is based on hardware and software co-designs. And the idea is to push as much as possible to the software side of the architecture, such that the hardware cost is minimal while retaining just enough hardware to make sure that the attestation software, the software implementation of attestation, can still run and operate securely, and with the same security guarantees of more expensive hardware-based techniques. And this is more applicable to lower-end IoT devices, but it still requires some hardware modifications, which is not always possible. And at the other end of the spectrum, we have software-based attestation. And this particular type of attestation method doesn't require any hardware modification, so it's very friendly to already deployed devices, which are the majority of the devices. However, since the device might itself be compromised, you cannot even store secrets on the device if you don't have customized hardware support to store secrets, right? So software-based attestation is typically implemented without keys or without secrets, and therefore there's no viable means of authentication. And instead, you have to rely, for example, on some assumptions that may be unrealistic for IoT settings. For example, you have to rely on a tight communication delay between the verifier and the prover, which basically translates to having the verifier directly connected to the prover one hop away. And this is, of course, unrealistic for IoT settings where devices communicate over the internet. So one hop further from software-based attestation, there's an architecture called Simple, which is basically a software-based remote attestation architecture that emulates hybrid attestation guarantees by using software virtualization. However, simple still requires secure initialization of the device to load secret keys to the device. And that itself is already also a problem, because you have to have manufacturing access to the device, and it doesn't really apply to devices that are already deployed. So the point is that none of these techniques, none of these types of attestation are really well suited for CPS scenarios where neither hardware modifications on every single prover on your IoT application, nor secure key initialization is possible. And that motivates our proposal for delegated attestation. So what is delegated attestation? So it's a technique that hopes to bring the best of both worlds by still allowing attestation to happen remotely, meaning that it can be done over the internet, which is not the case in traditional software-based attestation. You have to be one hop away in those cases, and but still allowing commodity and modified legacy provers as software-based attestation does. So targeting these provers that cannot use hardware or hybrid remote attestation. And the setting we envision is the one in the figure here, where you would have some local IoT network where multiple provers are connected to the same gateway. And these are unmodified provers. And what our scheme envisions is that we would add this, what we call attestation proxy. This is one additional device on the local network. And this device, it has to be capable of performing proofs of execution, which I'm going to explain in details in the next slides. All other provers would remain unmodified. And the important thing here is that this device is not really a verifier, because the verifier is elsewhere connected to this local networks over the internet, and the verifier is just assumed to be trusted, right? And in this case, we don't want to make this assumption. We want to connect this proxy device, and we want to assume that since it is in the local IoT network, that its software may be compromised, but not its hardware, right? So what is proof of execution in one slide, right? Proof of execution is basically a cryptographic binding between the proper execution of some code that can be arbitrarily chosen by the verifier, any outputs produced by this execution of this code, and a temporally consistent remote attestation of the code and its outputs. And temporally consistent here means that neither the code nor the outputs could have changed in between its execution and production of the outputs and subsequent attestation thereof. So basically, it gives you an authenticated proof that some output was produced by the proper execution of the expected code. And this can be implemented in very cheap devices. In particular, it has been implemented on the MSP430 microcontroller. So this is the type of device that we envision that you would add to your IoT setting to enable that delegated attestation. And it's secure under full software compromise. For the details, you can check the Apex paper, which discusses this in details. So assuming we have a device capable of generating proofs of execution, this is what a delegated attestation protocol would look like. And let me walk you through the details here. So on the top, we have our three types of devices: the verifier on the left, the proxy, which is the proof of execution capable device in the middle, and one or more provers. In this case, we only represent one on the right. And the idea is that the verifier is connected to the proxy through a remote connection, for example, the internet, and the proxy is in the same local area network as the provers. Therefore, the proxy and the provers can have some, what I mentioned in the beginning, a one-hop communication delay. And that's an assumption here. So probably this would only work in a wired network, because wireless networks may have variable communication delays. But settings where this would work, for example, will be a CAN bus, which is pretty predictable in terms of delay. And the basic idea is that the verifier would request from the proxy a proof of execution for the software attestation verification algorithm. And it will issue a particular deadline for this proof of execution to be done. And then the proxy that may or may not be compromised, but proof of execution is presumably uncompromisable, is responsible for producing a valid proof of execution. And to do that, the proxy must interact with the prover as specified by the underlying software-based attestation algorithm. It has no choice, otherwise the proof of execution would fail, right? And then the prover, just in any regular software-based attestation, it doesn't matter which one, really, would follow the protocol and reply with the attestation to checksum. And the point is that in verifying the validity of the proof of execution, the proof of execution already gives to the verifier the certainty that the proxy respected the time bounds in the software-based attestation algorithm, which is key for the security of the underlying software-based attestation algorithm. And then by checking both the proof of execution and the time bound that was issued as a part of this proof of execution, the verifier can know that the proxy really respected the time bounds of the software-based verification algorithm. And therefore, it basically allows the proxy, despite being potentially compromised, to emulate the physical presence of the verifier in the local network, the same local network as the prover, as it would be required in a traditional software-based attestation. However, the verifier is no longer required to be physically present. So that's the main idea. And this is supposed to really work with any software-based attestation algorithm we choose to implement with SWOT, and we report several results based on that. And we also propose a modified version of Simple that I mentioned in the beginning that doesn't require preloading of keys and also alleviates some code optimality assumptions that are required by software attestation. And please refer to our paper for details on those cases. So we did evaluate this extensively over Canvas network, which was our main target for this particular type of application, this particular type of protocol. And we implement this with 16 provers running simultaneously in one local network and one proxy device. And we discuss ways of synchronizing the responses such that everyone can respond and you can still have guarantees about absence of malware in the network as a whole. All of the details are in the paper. And in conclusion, I just want to mention that our goal is to bridge the gap between remote attestation and one-hop software-based attestation. In doing so, we do require one additional device to be added to the local network, but we no longer require a modification to every single prover in this network. And the key idea is to leverage proofs of execution to enable scalable remote attestation of commodity CPS without per device modifications. Thank you for listening, and please do let me know if you have any questions.
Okay, thank you for the presentation. So again, if you have questions, please post them in the Slack channel. So then we go to the third presentation, which is on direct anonymous attestation on the road, efficient and privacy-preserving revocation in CITS. The speaker is Benjamin Larsen. Benjamin is a PhD student at the Technical University of Denmark in the section for cybersecurity. And Benjamin will present live, if I'm not mistaken.
Thank you very much. Let's see if we can get this to work. And you guys can see my screen. Fantastic. Right, thank you. My name is Ben. I'm going to present this paper where we're going to look at revocation in the vehicular domain. I, of course, didn't do this by myself. I had some very good colleagues, Vanhoef GNSS from Ubitech, Janis Konteris from Huawei. I'm sorry, Janis, I can't the last name. And Kenneth Goldman from IBM. So let's move on. So the first thing we need to think about here is, why do we need this? So in a cooperative intelligent transport system, vehicles are speaking with each other. And this is very good for safety of cars, of course. It's very good for them to say, I'm going over here, okay, then I'm going over here. But you also need to make sure that the messages are authentic. And with authenticity comes the question of privacy. Think about you driving down the highway, and every meter you say, I'm here, now I'm here, now I'm here, now I'm here. And then an adversary is standing just with a radio receiver and saying, okay, okay, you're there, you're there, you're there. And then because a vehicle is so strongly linked with you as a person, you could basically say, oh, there go Ben, he's going at work again. And this is, of course, an issue. So what we usually do is we could use short-time identities. So for example, pseudonyms. So we had maybe 1,000 small identities, and we'll just change the identity every time that we send a new message. This is really good for privacy, but we start to have problems when it comes to revocation. Because if all of these are unlinked, then you have the issue that you need a very large certificate revocation list. And what we can see is up to multiple gigabytes. And think of a VW Polo with a 2 GB revocation list. That's never going to work. So one of the solutions is using a technology called direct anonymous attestation, which is built on trusted computing technologies. And with this, the prover can sign something and the verifier can see, okay, it actually came from a valid TPM, or in this case, a valid vehicle. But again, we have problems with the revocation. The way we can revoke a DAA key is having the issue to say, I don't want you to do this anymore. I'm taking your pseudonym master key, so to say, and you can't use that anymore. First of all, we might have pseudonyms that we already created we could use, but second of all, this is a very fierce operation. If this was just an issue with you had some sensors going a little bit off and you just needed a timeout, then you're now forcing that vehicle to go through a complete registration process with the issue again. And this is not always a good thing. So we're not really focusing on misbehavior detection here, but we want to focus on how we can revoke unlinked pseudonyms while still preserving the privacy of the vehicle. So just to get you the general idea here, we have let me just get a pointer on here. We have our trusted component, in this case, a TPM. We'll talk a little bit more about that. And this is a part of the vehicle. So the trusted component and the issuer, which is normally the manufacturer of the trust component, they talk together and make sure, okay, it's a good trust component. It's not on any list. I will accept you and you can get some credentials here. Then it will use the credentials to create some pseudonyms. And the vehicle can then use the pseudonyms to sign messages using the trusted component. But before he can do that, he will need, at least in our protocol, to register these pseudonyms, or at least the public part of it, with a revocation authority. And this is completely anonymous. Alongside these pseudonyms, or at least the public keys, it will send some data that is being used for revocation later on. But just keep that in mind. So at some point, the revocation authority decides to do a revocation, it will broadcast this information and the pseudonym out, and the correct vehicle will then execute or all vehicles will try to execute the revocation, but only the correct vehicle will succeed. So the TPM, as we heard in the previous talk, is a trusted module, and yes, they are expensive in the case of a fire alarm, but for a vehicle, $25 to $40 is not a lot. They're very small, as you can see also on the picture, and it's basically a system on a system. It has persistent memory, volatile memory, and a cryptographic processor. And it has a lot of great functionality. It can be used for a lot of different stuff. But what we're going to focus on is these conditional operations, policies. So with a policy, we can protect entities inside the TPM. For example, we can say a register may only be read under these circumstances, or a key can only be used if this happens and this happens. In our case, it's pretty obvious that we have pseudonyms and they may only be used if they're not revoked. And that's pretty straightforward, right? You'd think so. But as you shall see, it's a bit more difficult. Of course, the TPM must then manage the revocation state of each pseudonym. So what we do is we create a register inside the trust component, or we call it a revocation index. And for each pseudonym, we have a bit. So for pseudonym 0 here, we have bit 2. For pseudonym 1, we have bit 3. And if you want to use bit 3, bit 1 must not be set and bit 3 must not be set. And the reason why it's linked to 2 bits is because if you set this bit high, then this is revoked, then you have a sub-revocation. But if you set this bit high, then neither of these keys can be used because they both depend on this also to be not set. This is how we can define a hard revocation or a soft revocation. Yeah. So just to give you an idea how this works, I'm not going to go into details, but if we want to use a pseudonym for signing, we'll start by loading it into the trusted component. So now we are inside an area where we can't do anything in a malicious manner. We'll simply get a handle back, and then we do some management stuff. And now we know we need to comply with this particular policy that this bit in this register must not be set. So we are saying to the TPM, dear TPM, I have bit 1 and bit 3 in my policy on this key, and I need you to check if I can satisfy the policy. So the TPM will read the non-volatile memory, in particular the revocation index, and then it will execute an operation updating an internal register if the bits are not set. If they are not set, then this operation cannot happen. If you were providing the wrong bits in here, then the internal states will not be updated correctly. So you'd not be able to use this particular key. So it's basically impossible to try to cheat this system right here to make a signing operation with a pseudonym that's in a revoked state. So that's the simple stuff, the sealing or getting a key to only work if it's not revoked. How can we make sure that we actually keep that state? So if a key is revoked, it will always be revoked. Of course, not even the user should be able to write into the revocation index, because then the user can simply just, remove it. So the policy for writing to the revocation index is that the revocation authority will have to sign the command being executed, for example, set bit 1 in register 1. This have one very big, or it's two, but we're going to focus on one big problem here. The revocation index, or the revocation authority needs to know the name or the digital fingerprint of the revocation index. That means for two pseudonyms that share the same revocation index, it would be able to see, oh, they have the same index. Then they must come from the same car, and we don't want that. So what we're doing instead is when we're creating these pseudonyms and assigning them to a bit, then we are pre-computing a hash, a command parameter hash. So a command that says, set this bit or set this bit and this bit in this register. And then we are taking these hashes and giving to the revocation authority during registration. And this can be seen here. On the left side here, we have the command parameter hash, the hash of set bit 2. And over here, we have the hard revocation hash where we set both bit 1 and bit 2. So the final policy for accessing the revocation index is a combination of the small policies for each pseudonym. So either you must provide a hash over this command parameter hash signed by the revocation authority, or this command parameter hash signed by the revocation authority, or this command parameter hash, and so on and so forth. And that will be for all of the different pseudonyms. There's one problem here, however. We cannot apply this policy directly to the revocation index, because the digital fingerprint or the name of the revocation index depends on the policy that protects it. But the policy here also depends on the index, because it's depending on which register to write in. So we'll have a hash loop. So we have to figure out some other way to do that. What we're going to do is we're going to protect the revocation index by another policy. This policy authorized, states that any policy that is signed by this key, the authorization key, can be used as a valid policy to access the revocation index. So we can simply sign the final policy with this key instead. Now comes the problem. What if the adversary simply just takes this key and signs a policy he can comply with? That's a problem. So we need to ensure that you can only use this key once. The way we're doing that is we're creating yet another index. We call this the authorization count index. It has a secret and it has a maximum number of authorizations. Then we are creating a policy that's protecting this key that says, if you want to use this key, you must prove that you know the secret to this index, and that would require one authorization. That means you can only use this key once, because you can only authorize to this index once. Then the clever listener would say, well, can't you just reset the authorization counter? Yes. That's why, for example, during production, you would protect this authorization count index by another policy that would require a nonce to be signed by an ephemeral key and a very short-lived key. And we do that by putting it in a volatile index or volatile position inside the TPM, and then we reboot the TPM after we have done this. Then we will never be able to recreate this key again, and therefore we will not be able to reset this. So we'll only be able to use this once, and we can make sure that only if you can comply with these policies, you're able to write to the revocation index. So just a short wrap-up of our evaluation. We wrote this in C++. We tested it on a range of different TPMs, including the automotive models. Unfortunately, we had some issues with the SPI interface being rather slow, so we finally executed it on a laptop using an SLB 9670 TPM from Infineon. We saw some irregularities with some commands, so we compared it with Nuvoton TPMs and found that there are differences on the TPMs. Then we ran it 1,000 times and we got these results. So, of course, the offline phases is not as important because they can be done before you're actually leaving or taking the car out for a drive. But I still think it's important to recognize that it's actually quite fast. You're initializing the authorization counter index. If you need more revocation indexes because you need more pseudonyms, the non-primordial authorization indexes takes 45 milliseconds more. You can read about that in our paper, why it does that. And the initialization of the revocation index takes 317 milliseconds. That's just creating it, assigning the policy. And then you have to activate it. That means you actually have to write to it. You have to write pure zeros. And that takes a little bit longer because you have to go through the policies. But the interesting thing is that both soft revocation and hard revocation takes extremely short time. 300 milliseconds, and that doesn't matter if it's one pseudonym or it's 100 pseudonyms. We have near constant revocation times because the way we have structured the revocation. There's a slight increase if you, I think it's 20 milliseconds if you come up to 1,000 and 40 if you have 3,000 pseudonyms, 40 milliseconds, so it's not a lot. So just to recap, what do? We have fast revocation. It's very fast compared to if you had the certificate revocation list and now you revoke this and you revoke this and revoke this. We've never disclosed the identity of the vehicle, not even to the revocation authority. It's only the issuer that can link the signatures. We're able to revoke all pseudonyms based on only a single anonymous pseudonym because the revocation authority has the hard revocation hash for each pseudonym. We don't have any certificate revocation lists. We don't have any complex distribution of the data, but we have to consider there's a trust complexity trade-off here because the offline phases, of course, needs to be executed correctly. If you want 100% guarantees that these are being executed correctly, you need to include the issue in this, so you have some verification that, okay, it's actually the right policies and so forth. But it also depends on the area of or the use case you want to use this, because as you saw, the offline phases takes 2.4 seconds, and after that you can't mess with the with what was done in the offline phase. So if you can trust those 2 seconds, then you can trust the rest of the time. But yeah, we want to use this on an actual ECU at some point and with a real DAA implementation, and of course we want formally verification of our protocol. And yes, that was it for me. Thank you. Let's see if I can stop sharing here.
Okay, thank you, Benjamin. So then we move on to the Q&A part of the session. And I saw that there were some questions in Slack. So let's start with the first presentation, which was given by Mohammed on FADIA. So the question is, first, somebody says, great talk, thanks. It appears that the score function is run locally on each prover. How do you prevent cheating by provers in the protocol? A prover can advertise incorrect battery levels, CPU types to avoid doing the attestation tasks. Also, do you have any analytical, theoretical bounds on the maximum number of selfish provers tolerated by your protocol?
Hi. Yes, so actually this is two parts question. So let me start with the first part. First, thank you for the question. It's a very interesting question. So actually, regarding cheating, so the idea, how do we prevent cheating? We do not actually. But what prevents cheating, if cheating is designed by changing and setting some malicious code to implement the cheating, then this will be detected due to the attestation code. So the attestation code will detect that there are some malicious activity on the software or changes in the software, which will actually be failing the attestation and detecting that this device is no more healthy. However, this is not a requirement to do cheating. So, I mean, there could be some types of cheating that does not require changes in the software, such as like, I don't know, like maybe using some fake batteries or different, some batteries that does not report or change in the hardware or something like that. This will not be able to be detected. So that's why what we did is that to simulate this and to see how much this affects us, like the cheating, how much cheating affects the network. And our evaluation, this is the second part question. So, so regarding the evaluation of selfish provers, like cheating provers, selfish are cheating provers actually. So normally they want to cheat to try to fake, to show themselves that they are not capable of doing things, so that they get exempted from doing things and save their resources. So these are selfish provers. But to evaluate this, we did some experiments, and we did not do analytics and theoretical things. And the reason behind this is that this depends a lot on the environment that you are simulating on. So for example, let me just give an example to show this, what my point. So the idea, if you have a network of devices with different battery levels, and then you are trying to see what is the effect of selfish provers, this depends a lot on the density of these provers. So if you have a small area and with a lot of devices around it, then a small amount of selfish provers will make a big problem, because this will make a lot of contention and collusions on the network, and trying everyone to access the gateway at the same time to submit his attestation and go offline and leave. But if you have like a wide area with less density, then selfish will not affect a lot. So it depends on the environment they have. It will be, you get a different result there. So that's why we did an experiment with the same setups that we used before to measure this impact in such scenario. And that's what we did. I hope I had answered the question. And of course, if there's more about this, I can continue on this offline. Thanks.
Okay, thanks a lot, Mohammed. In the meantime, another question popped up. So Alexandra asks, FADIA uses some score to distribute the work fairly between the devices. How the readings about the energy level on the devices are obtained securely? Is some extra security mechanism required? If an attacker can manipulate the readings, a device with 5% energy could get more work than it can handle.
Indeed. So the idea, this is reported by the prover, and we trust the prover. What does he report? And that's why there's a possibility that he cheats. And that's exactly what we were saying. So there's the possibility that a prover can cheat, and he can cheat about what his own energy. And we showed how the impact of this would be. The problem here is that you cannot detect this unless you do some, I don't know, like some sort of detection algorithms, heuristic detection algorithm. If this cheating is involved while changing in the software, then this will be detected, of course. But if it's involved by doing some other stuff, then you need to do some heuristics, like for example, a sudden change in the battery, then this will be detected in a different means. It's not the remote attestation protocol who will detect this. So the idea, yes, this is an open area of research. You are both pointing to a right point, which is an open area of research. How do you trust what the prover is actually reporting? We, at this point in our experiment, we showed the impact of this. And the idea of how do we mitigate this, how do we detect these such behaviors, and how to prevent them is another area of research, which covers a lot of other topics as well. I mean, not only a remote attestation. This is a big area of research, which is a very interesting one. Thanks.
Okay, thank you. And then I have one more short question, since I don't see anything in the Slack anymore. So the scheme that you propose allows to improve load balancing also in collaborative remote attestation. But what would you do in a network where you have devices with intermittent connectivity, like those that are powered through energy harvesting, for example, and that might sometimes also be like offline or unavailable? Would your scheme be able to deal with that, or would you need like additional features?
Sorry, can I ask you to repeat? Can you please repeat the question? So I didn't get the part which. Sorry.
Yeah. So the question is, like, if your scheme would also be able to deal with networks that consist of intermittent systems. So systems that are not continuously powered, for example, because they rely on energy harvesting. So they might be just down or offline for some part of the time.
Yes. So the idea, yes, this would work, but you cannot guarantee. This is a common assumption in remote attestation protocols that are trying to detect attacks such as hardware attacks. So you cannot, in such network where your device may go offline and then come back online after some amount of time, you cannot guarantee that these devices are not manipulated. There could be some manipulation, hardware manipulation of the device, maybe some release of tamper-proof devices, and looking at the secrets, and everything will be compromised. You cannot guarantee that, and you do not have any guarantee against this using remote attestation. What you can guarantee is that while the device is in the network, it is not attacked, but outside of this range, you cannot do any sort of guarantees. And that's why what we do is we put an assumption that the device should attest in a period of time, like every period of time, it should report an attestation. And during this period of time, we assume that the attacker, this is a configured period of time, the attacker could not, does not have sufficient time to, during this period of time, to take the device offline and release the tamper, take the secret keys, and release and reveal the values. So this is the idea. Like normally this is 10 minutes, 20 minutes, something like that. During this 10, 20 minutes, you have no requirements. This device can go offline, but it should come back during this 10 minutes at least one time. That's the only assumption. You should go back online. So yeah, I hope this answered the question.
Okay, I see. Thanks a lot. And thanks for answering all the questions. Thanks again for your presentation as well. So then we move to the second talk. For now, I don't see any questions in the Slack channel. So if you have questions, please post them there. In the meantime, let me see. Yes. So I was wondering what kind of threat model and available security features you are assuming in the channel between the proxy and the end node, because I can imagine that there could also be an attack in this communication channel.
In the channel itself, yes, that's correct. Yep. There's no assumption on the channel besides what's required for this to work in practice, meaning you assume that you know the shortest communication time, and that the assumption on the channel is that every message you send is close to the shortest communication time, such that you can enforce a strict upper bound on the response time coming from the spoofers, the end nodes. And this is required by software attestation algorithms, irrespective of the delegated attestation setting. So the assumption is that the jitter, right, the variation on the communication delay is small. And is small enough such that any variation caused by, for example, malware that infects the prover, the end device, and tries to hide itself by copying itself around memory or something like that, or relocating itself to another device, that will take more time than the typical variation of the communication delay. And therefore, any such action will be detected, right? And this is not an assumption, this is not required by the scheme itself, is required such that one can tell the difference between a normal communication delay variation and an adversarial one. Like the adversary taking more time to reply to the attestation request, so that it can relocate itself or hide in some way. So that's the only assumption. But no security feature, no adversarial silence, nothing as such. And this is limiting because typically in a wireless setting, right, the delay can vary a lot. So you wouldn't be able to tell whether this is some adversarial action or if this is just a natural delay because, I don't know, someone turned on the microwave or something like that, right?
But the delay is the same for all nodes that are attached to the CAN bus, right? So if two devices would use root, then one could impersonate the other or not.
Yes, absolutely. And this is one of the things that I don't discuss in detail in the presentation. But the idea is that when you have multiple devices in a CAN bus, for example, right, they have to take turns to reply. And in order to make sure, you want to attest the network as a whole, right? And in order to make sure that one device is not assisting the other device, what you have to do is to make sure that they are always busy until their turn. So this is essentially kind of using a proof of work because each one of them has to reply at a given time. So you make sure that the device that replies second is busy until it's time to reply and compute attestation. So you make the last device, the cost of attestation higher to the last device to reply to make sure that they're always busy. And you have to keep all the computational power on your network busy until all the replies are brought back to the verifier. And that's how you make sure that there's no one device assisting the other device in the case where you have multiple proofers.
I see. Okay, thanks. And maybe one last short question. So the proxy, what kind of device is this? Like, what are the essential components that need to be there to support the proposed scheme?
Mm-hmm. Yeah, so the essential cryptographic building block or feature that is required by the proxy, it's something called proof of execution, which is it's essentially an extension to regular hybrid-based remote attestation architectures that allow you not only to attest some software, but also to prove that the software has executed correctly and produced some output. And this is what's required there. This proxy device is not assumed to be uncompromisable in terms of software. But if you have the proof of execution feature, which is kind of similar to what perhaps a TE could give you, but in embedded systems, right? And this is, if this is implemented correctly, it should be secure under software compromise as long as the hardware isn't modified. And then the one key idea is that it has been shown that you can do this even in very cheap embedded systems, even in something like MSP430, which is a $1 microcontroller. But this one device, this proxy, is one device that's purpose specific and it has hardware modifications in itself. The idea is that you only add that one instead of having to redesign and remanufacture all provers in your network.
Okay, thank you. And thanks for answering all
the questions.
For the presentation. Then we move to the questions on the third talk, and I saw there were a few in the Slack channel, so these are for Benjamin. First question was, do you assume that the cars are always connected? If yes, can the attacker try to prevent the revocation information from being propagated by using, for example, jamming?
That's a fantastic question, really. It's something we've also discussed, because not only jamming, but think about, you do not trust the vehicle in this setup, right? So what if the vehicle just decides, you know what, I received this message, I don't want to forward it. This is a general problem when we have a host that needs to forward something to a secure area. There are, of course, ways you can make sure this doesn't happen. For example, you could say every vehicle should, upon reception of a message, do a lock. You can set the TPM to lock everything and then send that lock signed back. But of course, then you have other questions. If you don't want to be able to track vehicle, can you track vehicle based on the logs and so forth and so forth? But this is a general problem. And one of the things people have talked about is, can you somehow randomize the data so the hosts don't know what's being executed? But so it really just have to execute everything and hope it's not a revocation message. But yes, it is indeed a problem, and an attacker could potentially jam the signal. That's like any other network. So that's also one of the steps that we need to take. Yeah, but that's a really good question, a nice observation.
Then there was one more question. So a nice talk, thanks. I apologize if I misunderstood your work here, but can the binary list of revoked pseudonyms be used to track the vehicle even if the individual pseudonyms are anonymous?
So there's not really a list of revoked pseudonyms. If the revocation authority gets a message on one pseudonym, it will say, okay, I need to do hard revocation with this one pseudonym. So I take the hard revocation hash that was provided during registration, and I'll broadcast that out. That will revoke all the linked pseudonyms inside the trusted component. So there's not really anything you can track here. If your question is about whether if you have all of the soft revocation hashes and hard revocation hashes, would you be able to link those? No. Of course, you could do some timing attacks if all of a sudden 64 pseudonyms are being registered. Well, the case is they're probably from the same car, but you will not be able to, only based on the hashes, be able to say that these are linked together. I hope that I understood the question right here. But there's no like a binary list of revoked pseudonyms like you have in certificate revocation lists. That's one of the pros of this protocol.
Okay, yeah, the person that asks says now, okay, got it, thanks. So your answer was very clear. I see that we are also at the end of this session now, because it's 10 to, yeah, okay, because we've been going on for 1 hour. So I propose that we end here. So thanks, Benjamin, for answering the questions and also for your live presentation. And thanks to all the speakers in this session for giving their pre-recorded videos or the live talk and for answering the questions in a very nice way. So with this, we end this session. If you have more questions, I think you can still post them in the Slack channel and the authors can still reply, I assume. So thanks a lot.
So hello, everybody. This is the beginning of our next session. This is the last session of today. And yeah, so today we have a crypto session, and in this session, 4 excellent papers will be presented. And I would like to remind you how we are going to handle Q&A sessions. So we are not going to ask them as usually is done at the end of each talk, but we are going to collect them in the Slack channel and have a special time devoted to this at the end of the session. And the first talk is going to be the paper presented by a PhD student at cybersecurity at Northern University at Boston, Marinos Vombas, and he's going to present the paper Selest Secure Elevation Estimation of Drones using MPC. And this paper focuses on privacy-preserving localization based on secure multi-party computation techniques. So the stage is yours. Please start the presentation.
Hello everyone, my name is Marinos Vombas and I'm a PhD student at Northeastern University. In this talk, I will be presenting Selest, a joint work with Eric Oliver Blas from Airbus and my advisor Guevara Nubir. Nowadays, drones have a major presence in our everyday life, for hobby or commercial purposes ranging from videography to marketing and even surveillance. This has also led to many instances of drones used in an adversarial manner, endangering public or private spaces. Organizations like the FAA and the EASA have imposed several restrictions for drone flights, and various mobile applications have been developed to aid drone users with regulations in their area of interest. However, there is no way for these organizations to monitor and enforce these restrictions in real time, which poses major safety concerns in areas such as airports, military bases, and public venues. Selest is an RF-based drone localization system aiming to detect the unlawful presence of drones in restricted areas without compromising the location and data privacy of other nearby emissions. RF-based approaches are commonly used towards drone localization by estimating the direction of arrival of the drone's downlink video emission. We start by describing traditional direction of arrival estimation techniques. The received samples from a single antenna do not provide enough information regarding the location of the source. However, by combining inputs from multiple antennas, we can analyze their phase difference and estimate the signal's direction of arrival. More generally, in arbitrary antenna arrays, the expected phase differences of a received emission from an angle phi is described by the so-called steering vector alpha of phi related to that angle. Therefore, by inverting the relationship between the steering vector and the source angle of arrival phi, modern techniques perform an exhaustive angle search to identify the range, elevation, and azimuth angles that produce the observed phase difference. In real-world scenarios, the received samples contain the collective information related to incident signals and noise. To address this complication, subspace-based direction of arrival techniques compute the covariance matrix and split it into 2 orthogonal subspaces, the signal and noise subspaces. Next, they perform an exhaustive angle search for the angle steering vector that has the maximum correlation to the signal subspace, or equivalently, the minimum correlation to the noise subspace. In particular, music is a popular subspace-based direction of arrival estimation technique that computes the correlation between the steering vector of every angle phi in order to produce the music pseudospectrum. The peaks of the pseudospectrum are the local minima of this correlation and correspond to the direction of arrival of the received signals, with the highest peak corresponding to the strongest signal, and so on and so forth. An important privacy concern is that such a drone localization system, aside from detecting the unlawful presence of drones, can be also inadvertently or deliberately used to track other surrounding emissions, such as legitimate drones, wireless networks, IoT devices, etc. This is where multi-party computation comes into play. MPC is a field of cryptography that allows a set of participants to jointly evaluate a function of their inputs without revealing anything else other than what can be inferred from the output. Let's see an example where Alexandra holds secret X and Beatrice holds secret Y. They first each come up with random shares of their secrets such that X equals X1 plus X2 mod P and Y equals Y1 plus Y2 mod P, where P is a large prime. They exchange shares so that Alexander holds X1, Y1, and Beatrice holds X2, Y2. By locally adding their shares of X and Y, the players produce valid shares of the result X plus Y. Addition and multiplication by a public value follow the same principle. However, multiplication of secret values is slightly more complicated and requires interaction between the parties. In general, addition is easy, performed locally by each party on the shares they hold. but multiplication is expensive in that it requires communication between parties, which is affected by the network latency. A common solution to this problem follows the offline-online paradigm, where correlated randomness is generated in the offline pre-processing phase and only input-dependent tasks are performed in the online phase. As an example, the beaver triples technique is commonly used for multiplication in MPC protocols as follows. Assume the parties have access to random secret values A, B, and C such that C equals A times B. In order to calculate the secret product Z of inputs X and Y, all parties compute and reveal D equals X minus A and E equals Y minus B and calculate Z as a series of local additions. Higher level functionalities can now be expressed as arithmetic circuits of additions and multiplications. In general, there exist various MPC protocols for different numbers of parties, adversary models, and computation domains. A significant distinction between types of adversaries is semi-honest adversaries that try to extract private information from the exchanged messages but always follow protocol, versus malicious adversaries that may arbitrarily deviate from protocol in order to compromise security or correctness of the output. Yau's garbled circuits is a particular case of two-party computation between a garbler and an evaluator. This approach, generally known as constant round protocols, is not affected by the multiplication depth of the circuit, but produces very large circuits, incurring heavy computation and bandwidth costs. Having discussed traditional direction of arrival estimation techniques and multi-party computation, we are now ready to present our secure drone localization system, which combines the two. In our approach, every antenna splits the received samples into additive shares and forwards them to remote servers so that no subset of servers have access to the original data. The remote servers then securely estimate the drone location by executing a multi-party computation protocol. We have two options for the output of our system. One is a coarse estimation of the pseudospectrum following traditional techniques, and the other is a conditioned output which returns violation when elevation restriction is violated. The first technical challenge that we encountered was the lack of existing implementations. Even though several MPC frameworks have emerged, their functionalities may be limited and none of them support complex arithmetic, which is a vital part of wireless applications. To this end, we implemented complex arithmetic in MPC and tested our system in two frameworks, MPSpeeds and EMP Toolkit. Our implementation supports fixed point scalars and basic as well as matrix operations. We also introduced our complex QR algorithm implementation using Gram-Schmidt process for orthogonalization and a fixed number of iterations. However, the additional MPC overhead results in more than 24 seconds execution time for a traditional implementation of music, which is prohibitive for the real-time constraints of a wireless application such as drone localization. To overcome this, we introduce a series of MPC-specific optimizations in our system and come up with two secure elevation angle estimation techniques for MPC. The first is optimized music, an optimized variation of the traditional music algorithm that achieves an order of magnitude improvement over a straightforward implementation of music in MPC. Second, we introduce Selest, our novel extension of music that achieves real-time performance by processing emissions one by one. In order to boost the performance of music over MPC, we first applied a couple of critical compiler-provided features of the MPSpeeds framework. First, throughout our whole system, we used parallel MPC communication for multiplications whenever possible. This effectively combines the data that need to be exchanged for multiple multiplications, reducing the communication run complexity of our system. Additionally, we take advantage of vectorized operations, which essentially applies a single operation of data in consecutive memory addresses, also known as single instruction multiple data. We also optimize the covariance matrix computation by exploiting the Hermitian symmetry in order to compute half of the matrix locally, reducing the required multiplications. Moreover, the aggregate covariance matrix is used instead of the average to avoid the unnecessary division. This only results in a scaled-up covariance matrix, which does not affect the eigenstructure of the matrix. We also revisited our complex QR algorithm implementation and minimized the number of multiplication-heavy operations such as norms, divisions, and comparisons. Finally, during the exhaustive angle search, we used the more efficient square norm expression and looked for the local minima of the denominator instead of inverting the expression and looking for the local maxima. Our optimized version of music achieves a significant speedup over the traditional implementation of music over MPC, dropping down to less than 3 seconds, which is, however, still prohibitive for real-world deployment. Modern machine learning techniques are able to detect, isolate, and classify RF emissions with high accuracy in real time. Selest assumes access to such techniques and relies on the assumption that the received samples belong to only one emission. Under the single emission assumption, we show that using a random vector from the span of the covariance matrix yields equivalent results as the noise subspace, thus eliminating the need for the expensive principal component analysis. Furthermore, Selest uses a modified steering vector that contains an average view of the original steering vector over f consecutive angles. We show that this provides a coarse pseudospectrum estimation that is equivalent to the average of the original pseudospectrum, but averaging the steering vector before the multi-party computation is crucial in the detection performance because it effectively reduces the exhaustive angle search by a significant factor. Finally, Selest provides two output alternatives. First, the coarse output only reveals an approximation of the emission elevation angle, and second, the conditioned output only reports a violation if the elevation angle is higher than a certain threshold. This, of course, incurs the additional cost of evaluating the violation condition inside the MPC circuit. Moving on to a summary of our results, we first evaluate the detection accuracy of our techniques. The first figure shows a view of the traditional music algorithm pseudospectrum, an average view of the original pseudospectrum, and the pseudospectrum view obtained by using Selest and our modified steering vector. We can see that our modified steering vector approach closely represents the average pseudospectrum of music, providing a close approximation of the angle of arrival up to a certain degree regulated by our modified steering vector. The next two figures compare the refined output of the traditional music to the coarse approximation of our two proposed techniques. These results come from a real recorded data of a transmitted tone, a Wi-Fi emission, and a drone. We next evaluate the effect of network latency on performance, and as expected, we observe a linear dependence of the performance on the network latency. We argue that a large portion of computation resources remain idle during the interaction between parties, which leads to a high potential for parallelism. Additionally, the second figure shows that garbled circuits still lag behind in arithmetic evaluation, mainly because of the large garbled circuits they produce, which need to be garbled, transmitted, and evaluated, resulting in high computational and bandwidth-related costs. Finally, we present a table of collective online throughput results and offline costs. For the online performance, we evaluated both our coarse and conditioned output for Selest in the single as well as parallel execution cases. We evaluated performance running multiple protocols with different adversary models, and we note for reference that for an honest majority of malicious adversaries, our techniques achieved 600 direction of arrival estimations per second throughput for the coarse output and 300 for the conditioned output. For an honest majority of semi-honest adversaries, Selest achieves almost 800 direction of arrival estimations per second throughput for the coarse output and more than 300 for the conditioned output. Finally, we analyzed the offline data usage for MPC protocols that require beaver triples for multiplication, as well as the cost of roughly $1 per hour for the creation of such triples in the maximum throughput case. Assuming a reasonable congested environment, we argue that our several hundred detections per second throughput are sufficient to maintain a real-time elevation estimation system that detects the unlawful presence of drones. To summarize, we introduce Selest, the first application of multi-party computation for wireless security. We evaluate the online and offline performance, computation, and network costs of our techniques for various adversary models in two MPC frameworks. Possible future directions include complex number arithmetic MPC optimizations, higher dimension direction of arrival techniques, and more MPC protocols specifically tailored to wireless applications. Thank you so much for attending the talk, and please feel free to ask any questions.
Thank you very much. That was our first presentation. I'm just looking at the Slack channel. At the moment, we don't have any questions. That's why we are going to proceed to our next talk. And I ask the audience also, if you get to any question later on, you can always put it also in the Slack. We are going to discuss the questions at the end of the session. So our second presentation, the title of the presentation is Julia, Fast and Secure Key Agreement for IoT Devices, by Franz Landerberg and Juraj Felian, and the paper is going to be presented by Juraj Felian. Thank you. And the paper addresses a very important problem, especially for IoT scenarios where we have very restricted devices in respect to computational power and also power consumption. And this scheme proposes a new key agreement protocol, which provides lower number of scalar multiplications compared to the state-of-the-art while achieving similar security properties. So the stage is yours. Please start the presentation.
Hello, my name is Juraj Felian, and I'm going to present the work done together with my colleague Franz Landerberg. We work at ASSA ABLOY, the world's largest manufacturer of mechanical keys and locks, but also the world's largest provider of access solutions, both mechanical, digital, and in between. ASSA ABLOY has been on a journey of evolution from being a traditional metal-based mechanical company into a digital knowledge-based company. I'm going to present our work on developing a fast and secure key agreement for IoT devices, which we call the Julia Key Agreement. We know that IoT devices are typically resource constrained. This does, however, not mean that we should sacrifice their security. We need for IoT devices to be able to communicate securely over insecure networks. The traditional approach here, still in use in many systems today, is using symmetric cryptography, where the devices are provisioned with a pre-shared secret. On the other hand, we have asymmetric cryptography, where each device is represented by a public key, while also holding a secret key. If a secret key is leaked, this only compromises this single device and not the whole system anymore, as was the case with symmetric cryptography. However, asymmetric cryptography requires more computationally intensive algorithms. So if we combine the two, we could leverage their respective advantages. And this is the approach in modern secure channels today. So in a secure channel, we first have an asymmetric key agreement phase where the two communicating devices together compute a shared secret. And this shared secret is never sent over the insecure network. After that, when we have the shared secret, we can use it to derive a symmetric key or symmetric keys, which are then used to encrypt and decrypt the communicated data. In our work, we have focused on the key agreement phase, so the asymmetric phase. The crucial operation here and the main contributor to the duration of a key agreement protocol is a so-called scalar multiplication. For the solutions developed at ASSA ABLOY, the application layer typically requires the following security properties from the secure channel: mutual authentication, forward secrecy, backward secrecy, and protection against key compromise impersonation attacks. The key agreement protocols that are available today require at least 3 scalar multiplications in the handshake in order to achieve this. We argue that a big benefit for IoT devices would be if we could achieve the same security properties with 2 scalar multiplications. And this is the main goal for us in the paper. Later in the talk, I will present the measurements that confirm that this indeed is a relevant goal. Before presenting our solution to the stated problem, we would like to show you the state of the art when it comes to Diffie-Hellman key agreement. In the paper, this is labeled as protocol P03. There we also have a more gradual introduction into the state of the art, and we show 2 simpler protocols first. But in the talk, we dive directly into P03, which satisfies all the stated security requirements, but does it with 3 scalar multiplications per party. This protocol is based on the noise protocol framework, which is a cryptographic library that has gotten a lot of attention over recent years. P03 is conceptually the same as the XX pattern in noise protocol framework. Okay, so let's take a look at what happens in this protocol. On the left-hand side, we have communicating party P1, and on the right-hand side, communicating party P2. We can see that the protocol is divided into 2 phases, the pre-handshake and the handshake. In the pre-handshake, we do the calculations that are necessary for each new communication session, but they don't depend on the party we will communicate with. This means that we could do these computations beforehand, store them on the device, and have them ready for when the handshake starts. And what this enables is that the handshake itself will be quicker.
In the pre-handshake, what both parties do is that they compute their temporary key pairs, or so-called ephemeral key pairs. So these are key pairs that are used per session, and after the session they are discarded. The lowercase letters are integers or scalars, while the uppercase letters are group elements. And a secret key is a large integer, while the corresponding public key is obtained by doing a scalar multiplication, denoted here with a star, between the secret key and the group generator. Unfortunately, we don't have the luxury of going into group theory in this talk, but in the paper we do have an introduction into cryptographic groups. When it comes to the handshake phase, the first thing that happens is that the parties exchange their ephemeral public keys. After that, they calculate the shared secret. And the shared secret has 3 parts. Each of these parts is obtained by doing one scalar multiplication. In the first part of the shared secret, the scalar multiplication is done between the secret ephemeral key and the other party's public ephemeral key. Then the second part between the secret ephemeral key and the other party's long-term public key. And finally, the third part between the party's long-term secret key and the other party's ephemeral public key. If, for instance, S1 would leak, this would still not make it possible for an attacker to pretend to be somebody else to party P1. This means that we have protection from key compromise impersonation attacks. Even if both long-term secret keys, S1 and S2, would leak, this would still not enable an attacker to calculate the shared secret without access to E1 or E2. This means that the protocol enables forward and backward secrecy. So the protocol does satisfy all the security requirements, but it does so with 3 scalar multiplications, while our goal is to do it with 2. This brings us to the core contribution of the paper, the Julia key agreement. In the pre-handshake, both parties calculate their ephemeral key pairs, which will be used in the next communication session. They also compute their respective T values. These are integer values that will be used when calculating the shared secret. In addition, party P1 calculates the H1 value, which is a hash of a concatenation of a string and its ephemeral public key. In the handshake, party P1 sends this H1 value to P2, and P2 responds by sending its public ephemeral key. This way, P1 has committed to E1 without having seen E2, and likewise, P2 has committed to E2 before having seen E1. This is necessary because otherwise it would open up for a man-in-the-middle attack that we detail in the paper. At this point, having received E2, P1 can calculate T2, do an integer addition, and then calculate the shared secret. Now, P1 responds by sending its public ephemeral key and the first application message, which is encrypted with the derived symmetric key. Technically, this is not part of the key agreement, but we show it here in order to demonstrate that the Julia key agreement only has a 1 round-trip overhead. At this point, party P2 can calculate H1 and compare it to the H1 value that it received in the first step of the handshake. If these values are the same, this means that P1 sent the E1 that it had committed to. At this point, P2 can calculate T1, do an integer addition, and then calculate the shared secret. The expression for calculating the shared secret is the core of Julia key agreement, and we call it the Julia expression. Here we have the Julia expression in its general form, then in the form that party P1 calculates it, and in the form P2 calculates it. If we look per party, we can see that there are 2 scalar multiplications in the Julia expression. Since the Julia expression contains some additional operations to the scalar multiplications, the question that can be raised is if it is faster to compute the Julia expression than the 3 scalar multiplications that we had in protocol P03. We will answer this question in the next slide by showing some measurements that we have performed. Before we do that, it's interesting to take a look at the Julia expression in its expanded form, together with P03. We could see that the parts of the shared secret from P03 are contained in the Julia expression. What we did here is we took hardware that is representative of ASA Abloy's products, and on this hardware we executed and measured the individual operations: scalar multiplication, group addition, integer multiplication, integer addition, and hash, as available from the libsodium cryptographic library. What the measurements confirm is that the scalar multiplication is by far the most costly operation. And then we took the measurement results and applied them to the individual handshakes of Protocol 03 and the Julia key agreement. And what we could see here is that the Julia key agreement is around 29% faster than P03. There is a lot more information available in the paper than what I was able to cover in this talk. We highly encourage you to read the paper and get in touch with us if you have any questions. We at ASA Abloy are firm believers in openly specifying security protocols, because the more they are used, tested, and probed, the higher the confidence that they are secure. What we haven't covered in this paper and what we want to do as a next step is a formal verification of the Julia key agreement. Thank you so much for your attention.
Thank you very much to the speaker. Let me see. So, yes, we don't have yet any questions to this presenter. So let me then announce the next presentation. The next talk is, the title of the talk is SNOW-V, an extreme performance variant of SNOW-V for low-grade CPUs. And the paper is going to be presented by Jin Yang. And Jin Yang is a PhD student from Lund University in Sweden. And this paper tackles the problem of efficiency for the SNOW-V cipher, which is a candidate to be included in the 5G standard. So the stage is yours. Please start the presentation.
Hello, everyone. My name is Jin Yang, and in this video, I will present our work, SNOW-VI, which is an extreme performance variant of SNOW-V for lower grade CPUs. So this is a joint work with Patrick, Thomas, and Alexander. Me and Thomas are from Lund University, while Patrick and Alexander are from Ericsson Research. So in my presentation, I'd like to first introduce the motivation of our work, then show the design and evaluation of SNOW-VI cipher, and finally give a short conclusion. In cellular networks, the confidentiality and integrity algorithms are used to protect the user and synchrony data between the users and the network, and this process is happening at the PDCP layer. There are 3 standardized algorithms in 4G for achieving this, which are AES, SNO3G, and SUC. They are all used for 128-bit security level and are usually implemented in hardware, thus can be very efficient. The table shows some performance results of these 3 algorithms, and we can see the speeds in hardware can be very high, higher than 50 gigabits per second, while the performance in software is not as good, especially for SNO3G and SUC. The speeds are all below 10 gigabits per second. But AES can still achieve decent performance. This is because AES has received hardware support from many CPUs. And here the speeds for AES are for the 256-bit version, and the speeds will be even higher for AES 128. When we come to 5G, 3GPP has asked Sage to evaluate and propose algorithms for 5G use, and this process is in progress. So for these algorithms, there are some new requirements. For example, they should be able to provide 256-bit security level to resist against quantum computing. At the same time, they should be able to provide a speed not less than 20 gigabits per second in the software. That is the target speed downlink in 5G. The reason why it should be in software is that in 5G, the PTCP layer where the encryption is happening is very likely to be moved to the virtualized part of a base station, and this indicates that the algorithms should be implemented in software. Well, in response to these requirements, in 2019, we designed a new cipher called Snowway as a new member of the Snow family. So the picture shows its structure. It follows the general design rationale of the Snow family with a linear part made of Elf shards and a nonlinear part called FSM, which is a finite state machine. So the Elf shard part has two Elf shards, Elf shard A and Elf shard B. Each of them has 16 cells, and in each cell there are 16 bits. Thus, we get 512 bits in total in the Elf shard part. These Elf shards feed to each other. For example, A0 is used to update B15, while B0 is used to update A15. And we have carefully chosen the fields to guarantee that such a construction can provide the maximum pure rate. So each time when update the Elf shard part, Elf shard A and Elf shard B are clocked 8 times, and after that 2 taps T1 and T2, which are both 128 bits, are sent to the FSM. So for the FSM part, it takes T1 and T2 as the inputs and outputs a keystring block Z, shown here, which is also 128 bit. After that, the 3 registers R1, R2, and R3 in FSM are updated. They are all 128 bit. So R2 and R3 are updated from R1 and R2 through 2 AES encryption rounds, and R1 is updated from R2 and R3 through some operations like XOR, addition, and permutation sigma. Since published, Snowway has received internal, external, and some public evaluation, and currently it is under the evaluation in the SAGE group. For its implementation, we can make full advantage of the same structure and the intrinsic instructions. For example, the instruction set for AES. So the table shows some performance results for Snowway, and we can say the speed in hardware can be as high as 1 terabits per second, and this is some result from a published paper. The speeds in software are all higher than 20 gigabits per second, thus satisfying the requirement of 5G. We can also see that the speeds are higher than those for AES as well. However, we received some feedback saying that the performance is not as good when the CPUs are less capable, for example, not supporting strong instruction sets. So we propose Snowway I to cover these use cases as well. So next, I will show the design and evaluation of Snowway I. We didn't make large changes from Snowway to get Snowway I. Actually, the FSM part remains unchanged, and we only introduced 2 small modifications in the Elf shard part. So the first modification is that now we use 2 simpler fields. Now each field has only 2 feedback taps. For example, the Elf shard A has feedback taps at A0 and A7, while previously in Snowway, each Elf shard has 3 feedback taps. The second modification is that now we have a new tap position for T2. That is, we move the tap position for T2 to the higher parts of the Elf shard A, while previously in Snowway it is tapped at the lower part. There are some many considerations behind these modifications. So For the new fields, the new construction can still provide the maximum period, but the construction is much simpler, thus the update cost can be reduced. Besides, the new construction can also allow for more efficient implementation. For the new type prediction for T2, we found with this modification, the cipher has better resistance against linear attacks, has better K and IV mixing effect, and also allows for more efficient implementation. So we did extensive evaluation of SnowVI. For the security, we revisited every cryptanalysis technique and found that the security properties are remained in SnowVI, and in some aspects they are even strengthened. For the performance, we tested the speeds in software on 8 different platforms with different capabilities. So these platforms support different types of registers from 128 bits to 256 bits, and different intrinsic instruction sets from the old SSE 4.1 to the latest AVX 5.12. We also tried the unrolled versions of implementations and found that the unrolling can further increase the speed. So the picture shows the performance comparison between AES, SnowV, and SnowVI. So the blue bars are for the speeds of AES, and the green ones are for SnowV, and yellow ones are for SnowVI. So we can clearly say that SnowVI has higher speeds than both AES and SnowV. So actually, the speeds of SnowVI are increased by 50% in average over SnowV in all these 8 platforms, and they are generally higher than 20 gigabits per second, even on the least capable platform P5. And the speed can be as high as 92 gigabits per second, and this is happened on platform P2. Besides, these implementations are very efficient and take very few instructions. For example, an assembly implementation can take as little as 15 instructions to encrypt 16 bytes in each iteration. So to summarize, we have designed an improved variant of SnowV cipher called SnowVI to cover more use cases, especially for those cases where the CPUs are less capable. So SnowVI only has 2 small modifications in the after part compared to SnowV, but with these 2 small modifications, we found that the security is kept while the performance is largely improved. So the speeds are increased by 50% in average and can be up to 92 gigabits per second. So for more details of the design and the performance, we refer to our original paper. So that ends my presentation. Thank you for the attention.
So thank you very much for the presenter. That was very interesting insights into future generation 5G networks. Let us now move to the next talk. The next presentation is going to be LNGate powering IoT with next generation Lightning micropayments using threshold cryptography. And it is going to be presented by Ahmed Kurt, who is a PhD student from Florida International University working at the Wireless and Security Lab. And in this work, the authors explored the ways to connect IoT devices to micropayment channels. And of course, it would enable many interesting application scenarios where IoT devices can, so to say, access payment channels and open many new applications. So I'm very excited to hear about results of this work. Welcome, and Ahmed, please take the stage.
Hello everyone, my name is Ahmet Kurt. I am a PhD student at Florida International University. Today I'm going to be presenting our work called LNGate Powering IoT with Next Generation Lightning Micropayments using Threshold Cryptography for WiSec 2021 Conference. This is a joint work between Dr. Suat Mercan, Ömer Slomovic, Dr. Enes Erdin, and Professor Kemal Akkaya. I would like to start with IoT machine-to-machine economy. We witnessed the fast adoption of IoT in numerous domains. IoT devices are now able to pay for received services, charge electrical devices, parking, and even sell their sensor data. You can see in the figure a broader picture of this machine-to-machine economy among IoT devices. So what is the micropayments challenge for IoT? IoT devices do not have enough computational resources to run LN or similar payment channel networks, and they cannot also use credit type payments because they introduce trusted third parties. Enabling trustless IoT micropayments will therefore open useful applications. We need therefore new lightweight payment solutions for IoT, and we advocate that LN is the perfect venue for this. Lightning Network is a payment channel network on top of Bitcoin. As you can see, Bitcoin is the first layer and Lightning Network is the second layer, and you can even have third layer applications on top of both. It solves the scalable problem of Bitcoin by enabling cheap and instant Bitcoin transactions. You can see in this figure a visualization of Lightning nodes across the world. It utilizes off-chain payments, which are not recorded on the blockchain. Only the channel opening and channel closing transactions are on-chain. We also use threshold cryptography in our approach, which deals with distributed cryptographic operations where more than one party is involved. Specifically, we use 2-of-2 threshold key generation, 2-of-2 threshold signing, and 2PHD child key derivation from the Gotham City white paper, as you can see in this reference. So in our system model, we have an IoT device that would like to send payments to destination LN node through an LN gateway. Since IoT device cannot run the Bitcoin and Lightning nodes, it's run by the LN gateway, and it charges the IoT device some service fee for this. Communication between the IoT and the LN gateway is wireless through the IoT gateway. And upon request from the IoT device, LN gateway opens a channel to bridge LN node and starts sending payments to destination LN nodes upon the IoT device's request. In our threat model, we assume that the LN gateway is malicious so that it can broadcast old revoked channel states to the blockchain. It can gather information about IoT devices, or it can try to steal and spend IoT devices funds in the channel. We also assume that any two parties can collude, and the communication between the IoT and gateway is encrypted and authenticated through a protocol such as TLS. Also, we consider these threats. Threat one is collusion attacks. Main motivation of these attacks to steal money from a third entity. We also consider stealing IoT devices funds, which is possible by the gateway through broadcasting revoked states or by collusion attacks. And we also looked at the ransom attacks, where LN gateway can become unresponsive and ask money to perform IoT's actions. In an LN channel, there are three main phases: channel opening, payment sending, and channel closing, which are explained through BOLT 2, which BOLT stands for Basis of Lightning Technology. In this figure, you can see an example exchange of messages between the funder and fundee for a channel opening. This is the outline of the channel opening in our protocol. Green steps, the ones are we added. So the main steps are basically IoT is requesting a channel opening to the gateway. Then a threshold key generation step is taken to thresholdize the Bitcoin public key, which also known as funding pub key. Then the funding transaction is generated. The first commitment point is generated through a 2PHD child key derivation. Then on this generated commitment point, new commitment transactions are generated by the gateway. A signature is generated between the IoT and LN gateway for this new commitment transaction. And then the funding transaction is broadcast to the network, and channel is locked and opened. For the sending payment, main steps are IoT is requesting a payment sending to the gateway. Gateway is creating an HTLC output, offering the HTLC to bridge. A new signature is generated in a 2-of-2 threshold signing. Then the old state is revoked. New commitment point is generated through a 2PHD. Then the payment success message is sent back to IoT. For channel closing, everyone can close the channel when they want, mutually or unilaterally. For IoT channel closure case, IoT can request a channel opening to the gateway, and gateway can choose to close the channel mutually or unilaterally. For mutual case, gateway and bridge will negotiate on a channel closing fee. Once they agree, they will create a closing transaction, and it will be signed by IoT and gateway in a 2 of 2 threshold signing, and it will be broadcast to the Bitcoin network. The on-chain fee for this transaction will be deducted from IoT's channel balance. For the unilateral case, the only difference is that the transaction that's going to be broadcast is gateway's latest commitment transaction. We also look at how to handle revoke state broadcast with our protocol. Normally, LN uses time locks to prevent cheating party from spending the funds immediately. Since we introduced IoT device, this will need to be revisited. We propose this commitment transaction for the gateway to prevent cheating and disincentivize basically. So if you look at the output one, it's for IoT's balance on the channel, and it's only spendable by IoT no matter what happens. Basically, even if gateway cheats and gets caught by bridge will not be able to get IoT's funds. And in the output for you see the gateway's fees on the channel. We made this output conditional such that if gateway gets caught cheating, it will lose the fees to the bridge, so it's basically disincentivized from cheating. This commitment transaction is generated after this following sequence of events. For the security analysis that we mentioned in the threat model, first one was collision attacks. There are three possible collisions. First one is the LN gateway and the bridge LN collision. This is only beneficial if LN gateway and bridge LN node have more funds in a previous channel state. But we see that this is never the case, as the payments are always from the IoT to bridge. Because of this, they don't have more funds in any previous channel state, which makes the collision infeasible. For the case where IoT device and LN gateway collude, it's only possible if the bridge LN node is offline. Therefore, this is a general LN issue and we don't address it. For the third case where IoT device and bridge LN node tries to collude, it's not possible because IoT does not know who the bridge is, as the bridge is chosen by the LN gateway. The second threat was stealing IoT devices funds. We handle all these three cases using 2 of 2 threshold scheme basically. For the ransom attack where LN gateway can become unresponsive, best case of IoT is just to wait and reject gateway's ransom request. So this way gateway will have to continue serving the IoT as it's making money out of this service. Our experiment setup is like this. So basically we modified C Lightning source code, and our code is publicly available at this link. We modified the HMCD module of the C Lightning mainly. It deals with the cryptographic operations. We thresholdized funding pub key and its associated Bitcoin private key. For the IoT device, we use the Raspberry Pi 3. For LN gateway, we use the Linux machine. For threshold client and server, we use Gotham City from Zengo. And for the IoT gateway, an AT&T fiber internet modem was used. For full Bitcoin node, we use Bitcoin D. And for wireless communication, we use 802.11n standard. Our first experiment was computational delays at the Raspberry Pi. Basically, there's one main operation, which is the 2 of 2 threshold key generation and signing. Threshold key generation took 1 second, threshold signing 153 milliseconds. As the key generation is done only one time, we can neglect it. Threshold signing is also negligible. Second experiment was the communication delays. Basically, this has the following components: delay of sending a request from IoT to gateway, execution time of the LN operation at the gateway, delay of the acknowledgement message sent from gateway to IoT. To compare these values to something, we also looked at the no IoT case where gateway performs everything by itself. You can see the values in the table. There's approximately 3-second difference between the IoT case and no IoT case, and no IoT case is quicker as expected. And these delays are coming from the threshold message exchanges between the IoT and the LN gateway. And the main interest of us is the payment sending time, which is around 4 seconds. We also analyzed the cost with our protocol. We've considered these following costs: the on-chain fee for channel opening and closing, the fees that are charged by the LN gateway, for the fees that are charged by the nodes on the payment route. So the channel opening fee for a two threshold signed transaction was only 222 Satoshi. And the channel closing fee was 183 Satoshi. These are basically negligible. And the gateway fees entirely chosen by the gateway. We will look at it later. And forwarding fees, we measured them to be 2 Satoshis, which is again negligible. So when we compare these to LN's original fees, when we don't use the threshold and anything, basically does not introduce any extra costs other than the gateway service fees. And we also looked at the network usage and bandwidth analysis. In this experiment, we investigated network usage between the IoT device and LNGate and the required bandwidth for the IoT device to timely compute the LN operations with the gate. We used IP-Traf software to inspect IP traffic on Raspberry Pi. You can see the interface of this software. Here we considered all main LN operations, and our measurement results show that the network usage was only 4,000 bytes. Considering that the payment sending only takes 4 seconds, then the required bandwidth will be 7.8 kilobit. Basically, this is as low as LoRa's bandwidth, which is very suitable for IoT devices. And finally, we looked at the toll payment use case evaluation of our protocol, where cars can pay the toll with LN payments using a built-in IoT device. Considering 802.11n used, which has a range of 250 meters, and cars are passing through the toll gate with a maximum speed of 80 miles per hour, then they will have around 7 seconds to complete the payment. Since our payment sending takes only 4 seconds, they will be able to pay the toll on time. Quickly looking at the fee analysis for the gateway, if toll is 75% per pass, gateway charging 5% fee, and cars are passing the toll 2 times a day, the total fee that the car will pay to the gateway will be $2.25 in a month. So considering that the credit cards also charging some service fee, this is probably in the same level as a credit card or even lower than a credit card. To conclude my presentation, basically we proposed a secure and efficient protocol for enabling IoT devices to use Bitcoin's Lightning Network for sending payments. We introduced a 2-of-2 threshold scheme to LN and modified LN's existing peer-to-peer protocol and introduced IoT device to LN channels. We achieved all these interactions with a gateway node, which has access to LN and provides the services in return for a fee. And our evaluation results show that the proposed protocol enables timely payments with negligible costs and delay overheads. Thank you so much for listening. If you have any questions, I will be glad to answer.
Thank you very much for our last speaker and generally to all the speakers who presented in this session. And now we are going to move on to our Q&A session. And we are going to start with the first presentation. And I would like to mention that our first paper presented here also was marked as having replicable results, and thank you for providing artifacts which help us to verify this research. So this is very valuable for the community. We thank you for that. And so now I'm going to look at the Slack channel. We have some questions there. Let's see what kind of questions we have for the talk number 1. The first question I see here is asked by Jasper Stang. He's asking, the way I understood it, Selest approximates the DOA estimation, which comes at the cost of location accuracy. Does this reduced accuracy has an impact in real world use cases?
Yes, thanks for the question first. Starting from high resolution direction of arrival techniques like music, we indeed can get very high accuracy in localizing targets in 3D space. And we adapted these techniques we optimized them for MPC, and they are feasible, but they are still a bit prohibitive for real-time performance. So they are okay for offline analysis of emissions, but however, they have still 2 downsides. First of all, they would still reveal the location of any received emission, either a drone that is violating some space or a random Wi-Fi or IoT device. So that's the first downside. And the other is the real-time performance. So in Selest, we actually optimize further for MPC and counter these performances by getting a rougher estimation instead of high accuracy. So we did go for lower accuracy. And even when we reveal the location of an output, it is not precisely, we reveal a rough estimation instead of the precise location. That's one type of output. The other type of output that Selest offers is a conditioned output that would simply output either a violation or nothing useful about the emission, the received emission. Both outputs however, completely hide the input samples that belong to the emission, the input to receive samples. So yeah, I hope that answers the question.
Thank you. I think Jasper can put in the Slack channel if he's satisfied with the answer. And while he's doing so, I can ask also a question. I collected some questions during your presentation. So we all know that like MPC might be not the best solution from performance perspective. You made good points arguing that you do achieve significant performance. You also used improvements that helped to achieve this performance boost. But the other problem is, especially for drone systems, is energy consumption. So my question is, did you analyze how that would influence the energy consumption and if it is feasible for this use case?
So may I ask, energy consumption of the actual receiving antennas, with the system itself?
Like if you compare this like techniques which were used previously as a baseline and you compare it to MPC-based solution, what would be the difference in energy consumption? So what kind of costs you pay for this solution for privacy in terms of battery life?
So just to clarify first, this has nothing to do with the battery life of the drone itself. We did not analyze the energy consumption of the receiving array, antenna array system, because we assume that in both cases, either via MPC or in plain text, let's say plain computation, a real-time system will be constantly plugged in and receiving emissions, decoding emissions. However, we did analyze the cost of processing the additional overhead that MPC incurs processing these emissions using remote servers. We used costs from Amazon Web Services, and we also used costs for network communication, because this is the main bottleneck in the MPC computation between the participants. So both
just the point is,
yes, please.
Additional communication would also cost extra energy, right? So like
right. So that's correct. So our system can be deployed in actually local servers. So the antennas may perform the MPC computation themselves, but in our proposed system, the antennas forward the received samples into remote servers, which are running on the cloud. We did not analyze the case that local servers do the additional computation and incur further computational resources and energy, yes.
Okay, thanks. And one small question at the end, you mentioned that you couldn't find existing efficient MPC implementations, so you had to implement things yourself. Do you make your implementation available as open source, or what are your plans?
Yes. Just to clarify, efficient complex number, but actually no complex number arithmetic. There are efficient MPC implementations. The first step is integer arithmetic, of course, and that would be the most optimized in multi-party computation. And then this is extended to fixed point arithmetic in all of the frameworks that we found. But then from there, support starts to be limited. We implemented complex number arithmetic, and all the code for the complex number arithmetic is already public, and it can be used to extend the MP speeds framework that we used.
All right. Okay. Thank you.
You're welcome. Thank you for the questions.
So if there are no other questions to the first presenter, let us now move to the second talk. let me remind you that our second talk was about the fast and secure key agreement for IoT devices protocol called Julia. And we have a question on Slack. It's also from Jasper Stang, and he writes, great talk. Have you measured the energy saving due to less color operations for certain devices, or do you have an idea in which magnitude it is? I think that's a well-motivated question, especially when we think about battery-powered locks, which are used, for example, by produced by ASA Abloy. So just to have the feeling if it is applicable, that would be good to know this answer to this question.
Yes, thank you for the question. And I would also like to add that we, in addition to battery-powered locks, we also have some energy harvesting locks, where it's, I would say, even more important to save on energy. No, we haven't done measurements with energy, but with all the systems on chip that we use, the energy consumption is directly proportional to the CPU time spent on computations. So I would say that we can get a pretty good estimate on the saved energy consumption just looking at the measurements that we have performed on CPU time, and there we get roughly 29% savings.
Okay, thank you. I think it is a good answer. Clarifies a lot, even though you didn't perform exact measurements. So I think we don't have any other questions in Slack, but I have some questions additionally collected for you. I am actually very pleased to see such papers coming from industry, and because you know, we often observe a gap between research and what we see in practice. And I have also experience with many door lock vendors working on different, you know, from our point of view, from researchers' point of view, like relatively standard techniques, which were perceived by industry as a, like, I don't know, like a rocket science. And my question is, do you think this kind of solutions could eventually end up in real products? How far is it, for example, in ASA Abloy?
Well, for us, I would say this is quite close. I mean, one of the reasons why we wanted to publish is because you know that security protocols, they're notoriously difficult to prove to be correct. And then the more people look at them, the more confidence you have that they are correct. So this was also our way to increase our confidence that this is secure, because we want more eyes on it. But I would say that it's quite, we have use cases where we want to use it, and it's relatively simple to implement it. So I would say for us, the step is not so far from this research paper to actually using it in a product.
Okay, that's great, and it's also very good approach to have open to work with open protocols, and we have so many security by app security broken systems. So I really appreciate your approach to deal with that. So thank you very much. Let me have a look if we've got any new questions. Meanwhile, I don't think so. So then we are going to move to the third talk. And let me remind you again, the third presentation was about Snow VI protocol, which improved the processing or like performance for the cipher, which is used in 5G. It's going to be used in 5G networks. We have a number of questions here for the talk number 3. The first one is from Sidhar Dongre. Sorry if I pronounce the name not completely correctly. She writes, thank you for your talk. Your results are very interesting. Out of curiosity, would you please mention the names of some of the platforms that you use to analyze the performance of Snow VI? For example, in the slide, there were P2 and P5 platforms mentioned. Can you just elaborate what platforms they are?
Yes. Actually, we had all the details for the 8 platforms and all the speed figures in our paper. So if one is interested, we refer to our original paper. But basically for P5, it is the strongest platform among the 8 platforms. So it is based on the Intel i7 CPU, and it supports the strongest instruction set, AVX 512, while P5 is the least capable CPU, which is based on Intel Pentium, and it only supports SSE 4.2 instruction set. And that is the reason why the speeds are lower on this platform.
Okay, but they are not so small, the platforms, right?
Yeah. Relatively, yeah.
Okay, all right. And then we have next question is by Merlin Hlosta. SNOW 5G introduces user plane integrity protection, but full rate support is optional with resource-constrained IoT devices in mind. Will SNOW VI enable more low-power user equipment to turn on user plane integrity, and or are the main advantages on the network side?
That's a good question. But I would say our design is not mainly for the hardware. I mean, not so lightweight for the resource constrained IoT devices. It's mainly for the efficient software implementation, mainly at the base station side. So at the user side, the implementation is still in hardware, but we did consider the hardware implementation in these devices. So even though it is not so lightweight, we would say the implementation would not be more heavyweight than AES. But if one wants to use some cryptography algorithms for the IoT devices, some more lightweight algorithms are needed. Yes, thank you.
Okay, thank you. There is one more question from Christina Pöpper. Your performance improvements are interesting. I'm wondering about the resulting security though. Would you say that SNOW VI is as secure as SNOW V, or that it is even more secure than SNOW VI?
Yeah.
Would you agree that most of the results received for SNOW VI are not affected by the new LFSR, may not fully capture all security implications?
Yeah, okay. So for the first question, I would not say SNOW VI is more secure than SNOW V. We just see that in some aspects, SNOW VI has better resistance against some attacks compared to SNOW V. But we won't say SNOW VI is more secure. And by saying that SNOW VI is as secure as SNOW V, we mean that they can both provide 256 bits security level, but that is based on our cryptanalysis results. Maybe in some future research, some people would propose some stronger attacks. So for the second question, I totally agree. So, but I would say most cryptanalysis results are kept, especially for those attacks which are mainly determined by the FSM part. So these attacks results remain, but for other attacks which might be influenced, we actually evaluate these attacks individually in our paper.
Okay, thank you.
Yeah, thank you.
Just a quick question. So you concentrated on improvement of software performance when implementation is software. Do you think your changes had any impact on hardware implementation? Do you need some, I don't know, other support in hardware for your algorithm?
Yeah. Hardware is also important, but we mentioned in our paper that the hardware will implementation will not be affected largely. They will be very similar to the hardware implementation of Snowway, and actually they should be even simpler since the update of the electrical part is simplified.
Okay, thank you.
Thank you.
Thank you. And now we are going to move to our last presentation. This paper is LNGate, powering IoT with next generation Lightning micropayments using threshold cryptography. And for this talk, we have two questions. The first one is coming from Murtuza Jadlibala, and she's writing, interesting talk. The IoT device relies on correct operation of LN gateway for good transactions always. So I'm not sure how this situation is better than the IoT device communicating with the credit card server. As a matter of fact, and an untrusted LN gateway could result in privacy issues. Have you considered the privacy issue in your proposal?
Thank you for the great question. This is actually a valid concern. I agree. I think we need to distinguish between the trusted and untrusted first, because like in the credit card type payments, it will be a trusted solution, and with our proposed solution, it's untrusted basically. So there's a distinguishment. But for the privacy side, I agree that to some extent, some privacy is being leaked to the gateway from the IoT. So it might get some data in the receive messages, in the send messages, in the interaction between the gateway and the IoT. There might be some privacy leakages at the very end. So I think we will look at it in the future, probably like as a future work.
Okay, thank you. So, and the second question is, thank you for the talk. A practical question regarding the toll station example on slide 21. If the transaction takes 4 or 7 seconds of the car being in reach, did you look into the time required for the connection setup with 802.11 under changing channel? And in particular, what would happen if it does not work quickly, so you fall below 4 seconds? And if it happens so often, is it an issue?
Yeah, I quickly tried to answer it on Slack. So this is a wireless channel issue, basically. So imagine a case like using a wireless solution like 5G, for example. It might not be as reliable as wireless 802.11n, maybe because of the coverage issues. And also you need to pay for it, like to have a SIM card and all. So probably we need to examine it separately. As in the worst case scenario, we might need to enforce the car speeds accordingly. So like, don't forget also, this is just a use case example. It might be adjusted based on the configurations of the environment, I mean. But the main protocol still works, and the issues related to use case, specific uses can be adjusted, I believe. So we use the wireless like 802.11n as a, since it's really also popular, that's why we use it basically.
All right, okay, so I think that's reasonable answer, probably depending on your use case. If it's not enough, you could reduce and force the cars drive slower over the gate.
Yeah, also one more addition. Imagine 8 miles per hour, also very, very fast. I mean, I don't really think that cars will pass through the toll with 80 miles per hour anyway. So maybe 15 miles per hour will give you like 11 seconds. So 11 seconds is more. Maybe it will be enough.
Okay, and I wanted to ask as well the question about if you think that the fact that IoT device is connected through single device, would it somehow impose the problems typical in blockchain systems like Eclipse attacks? Can the gateway somehow manipulate the view of the IoT device such that it is strict in doing something?
Okay, that's an interesting question. So basically, IoT don't have a a view of the blockchain, basically. So it's completely blind in terms of seeing the blockchain and transactions or anything. So, but for the gateway, basically, it has access to the blockchain, and also it's processing the transactions. It's a full node. It's running full node, and also serving many IoT devices. So your question is if it can be subject to Eclipse attacks by other nodes, I think, right?
Yeah, I'm just I couldn't really follow closely the details of the protocol, but if you rely on certain information which is obtained from the blockchain, yeah, I don't know, a nonce or something like this, and you process it, and for example, if it is transferred to the IoT device, the IoT device might be put in this situation, and it signs some, I don't know, incorrect message, etc. So I was just thinking if you consider this attack vector in your evaluation.
So I think what's going to happen in that case is just basically it's going to fail. The 2-of-2 threshold signing, it's just going to fail. It's not going to go through. So since it's an online process, also both parties need to be online at the same time when that happens, like when you are signing a specific transaction. So if the hash is incorrect or the transaction ID is incorrect or some details are out of order, so basically it's just going to fail. Or if you somehow manage to sign the transaction, it's not going to be mined by the blockchains at the very end. I mean, the transaction will itself be invalid, so it's not going to go through, basically. So I think that looks like a lesser concern, among others.
Okay, thank you. And with that, we are coming to the end of this session. That was the last session of today. And as next, we are going to have closing remarks. And thank you very much for attending the conference. And we are going to, after closing remarks, we are going to say bye to each other and see each other tomorrow in the new day of WiSec. Thanks and bye.
Okay, thank you, Alexandra. Thank you everyone for attending the second day of WiSec. First and for all, I want to remark that in case you missed the interviews of the demo and poster sessions today, you can still watch them, you can re-watch them on YouTube. So you can search on YouTube for WiSec demo and posters, and then you will find a playlist with all the interviews. So you can even watch it if you are purely watching our live stream on YouTube. And if you are a registered attendee, you can go to our Slack instance, to the demo and poster channel. And there you can find a link to the playlist that contains all interviews. And the actual demo and poster session will take place tomorrow on GatherTown. I also want to highlight that tomorrow we will have a panel on digital vaccination passports. And this panel will include Marion Braams, Thomas Loniger, Joanna Masel, and Bart Preneel. Finally, to conclude this day, I still want to encourage everyone to still try to meet on GatherTown. As Christina mentioned at the start of today, it's not part of our announced program, but the GatherTown instance is available throughout the whole WiSec conference. So I want to encourage you to use it during the conference, but especially right now. So I encourage you to open the Gather instance now to still walk around and interact with attendees and meet fellow people. And with that said, I hope to either see you on GatherTown right now, or if you are unable to make it right now, I hope to see you tomorrow. Thank you and have a good day.